Tonight, you're about to spend some time with one of the strangest objects in the universe. Not a planet. Not a star. Not even a galaxy. Instead, you're drifting towards something that appears to be absolutely nothing at all. Before we begin, get comfortable. Adjust your blanket. Find the cool side of the pillow if it still exists. Dim the lights, settle in, and allow your thoughts to slow down like distant stars disappearing beyond the horizon. Now imagine this. You've just arrived in deep space. There are no roads, no buildings, no traffic, and thankfully no emails waiting for a reply. Above you, below you, and in every direction around you, the universe stretches endlessly into darkness. Tiny stars glitter in the distance like scattered grains of silver dust. Entire galaxies drift silently across the cosmic ocean. And somewhere ahead of you is a black hole. At first, you don't actually see it. That's because the first sleepy fact about black holes is that they are, quite literally, black. Not dark gray. Not very dim. Not difficult to notice. Black. A black hole emits no visible light of its own. If you were floating through space looking directly at one, it would appear as a dark circular region against the brighter backdrop of stars. It's a little like somebody punched a perfectly round hole through the universe and forgot to patch it afterward. As you drift closer, you notice something strange. The stars behind the black hole don't disappear entirely. Instead, they seem warped and stretched around its edges. Light bends in unusual ways, creating a distorted halo surrounding the darkness. It's beautiful, also mildly concerning. The universe generally prefers its stars to stay where they belong, and yet here they appear twisted like reflections in a carnival mirror. Which brings us to sleepy fact number 2. A black hole isn't actually a hole. Despite the name, there is no tunnel, cave, pit, or giant cosmic drain hidden in space. Astronomers use the term black hole because early scientists needed a way to describe something that trapped light so completely that it appeared as a dark void. In reality, a black hole is an object. A real physical object with mass. An enormous amount of mass. Imagine taking something heavier than our sun and squeezing it into an unbelievably tiny region of space. The result is a gravitational field so powerful that it changes the very shape of the universe around it. Which sounds dramatic because it is. As you continue drifting forward, you begin to notice that movement feels different here. You aren't being pulled by ropes. There's no invisible vacuum cleaner switched on somewhere. Nothing is reaching out to grab you. Instead, space itself seems gently tilted. Like standing on a hillside without realizing it. This leads us to sleepy fact number 3. Black holes have incredibly strong gravity. Gravity is the force that pulls objects toward one another. It's the reason your feet stay on the ground. It's the reason the moon circles Earth. It's the reason planets orbit stars. And it's the reason you should probably avoid trying to park a spaceship directly next to a black hole. The stronger an object's gravity, the more mass it contains. Black holes pack enormous amounts of mass into very small areas, creating some of the strongest gravitational fields known in the universe. But gravity around a black hole isn't magical. It follows the same fundamental rules as gravity everywhere else. It's just operating on an entirely different scale. Imagine replacing the gentle slope of a hill with the side of a mountain. Then replacing the mountain with a cliff. Then replacing the cliff with something that causes physicists to stare thoughtfully out of windows for several decades. That's roughly the direction we're heading. Ahead of you, the darkness grows larger. The warped ring of light becomes more obvious. The stars seem to curve around the object in impossible ways. And somewhere ahead lies one of the most famous boundaries in science. The event horizon. This brings us to sleepy fact number 4. The event horizon is often called the point of no return. If you're safely outside it, you can still move away from the black hole. If you cross it, however, escaping becomes impossible. Not difficult. Not unlikely. Impossible. Even light, the fastest thing in the known universe, cannot escape once it passes beyond this boundary. Imagine the world's strictest exit policy. Now make it infinitely stricter. That's the event horizon. As you approach, the boundary itself remains invisible. There isn't a giant warning sign floating nearby. No helpful fence. No cosmic employee handing out safety pamphlets. The universe simply assumes you've read the instructions beforehand. The event horizon marks the distance where gravity becomes so powerful that every possible path forward leads deeper inward. For now, though, you're still safely outside. You drift quietly through the darkness, observing from a respectful distance. A very respectful distance. The sort of distance recommended by both astronomers and common sense. Around you, stars continue shining. Faraway galaxies glow softly. Clouds of gas drift through space like luminous rivers. And the black hole waits silently at the center of it all. Which leads us to our fifth sleepy fact. Despite what movies sometimes suggest, black holes are not giant cosmic vacuum cleaners. This surprises many people. A black hole doesn't automatically suck in everything nearby. If our sun were somehow replaced by a black hole of equal mass, which would create several new problems for humanity, the planets would continue orbiting exactly as before. Earth wouldn't suddenly spiral inward. The moon wouldn't shoot off into space. Your coffee mug wouldn't vanish into an interstellar abyss. Although the coffee itself might still disappear for unrelated reasons. Gravity depends on mass and distance. A black hole with the same mass as the sun would exert the same gravitational pull from far away. The difference is that all of that mass would be compressed into an incredibly tiny region. That's what makes black holes special. Not that they pull harder from every distance, but that they can pack extraordinary amounts of mass into astonishingly small spaces. As you float there in the quiet darkness, the realization begins to settle in. The universe's most feared objects are not monsters lurking in space. They're stranger than that. They're natural consequences of gravity. They don't hunt. They don't chase. They simply exist, patiently bending space, warping light, and challenging everything we think we know about reality. Ahead of you, the black circle remains perfectly silent. The stars continue their ancient dance around it, and somewhere beyond that dark boundary lies a region of the universe no traveler can ever return from. For now though, you're safe. You've made your first encounter. And this is only the beginning of your journey into the sleepy, mysterious world of black holes. You've now spent some time floating near a black hole. You've admired the darkness. You've cautiously avoided crossing the event horizon. And you've successfully resisted the urge to knock on it and see what happens. Which is good. Because black holes generally don't answer the door. But as you drift quietly through the cosmic darkness, another question begins to form. Where did this thing come from? After all, black holes don't simply appear out of nowhere. The universe doesn't wake up one morning and decide it would be nice to install a gravity monster between two spiral galaxies. No, every black hole has a story. And tonight, you're about to witness the beginning of one. As you turn away from the black hole, space around you slowly changes. The darkness gives way to scattered stars. Some are small. Some are medium-sized. And some are so enormous that our sun would look like an afterthought parked beside them. One of these giant stars glows ahead of you. Brilliant blue-white light pours from its surface. It's beautiful, magnificent, and completely doomed. This brings us to sleepy fact number 6. Many black holes begin their lives as massive stars. Not every star becomes a black hole. In fact, most don't. Our sun, for example, is far too small. When its life eventually comes to an end billions of years from now, it won't collapse into a black hole. Instead, it will quietly fade away after passing through several dramatic but comparatively civilized stages. Think retirement rather than catastrophe. The truly massive stars are different. These giants can contain many times the mass of our sun. They're hotter, brighter, more energetic. And unfortunately for them, they burn through their fuel at astonishing speeds. The cosmic equivalent of spending your entire paycheck 5 minutes after payday. For millions of years, the giant star ahead of you has been performing a delicate balancing act. Gravity is constantly pulling inward. At the same time, nuclear fusion inside the star pushes outward. These two forces compete endlessly. One pulls, one pushes, and for a while everything works beautifully. The star remains stable, bright, powerful, comfortably existing without accidentally collapsing into itself. Which, as life goals go, is actually quite respectable. But nothing lasts forever. Even stars eventually run out of fuel. This leads us to sleepy fact number 7. Black holes are often born after a star can no longer support itself. Imagine a giant campfire. As long as it has fuel, it burns brightly. But once the fuel runs out, the flames begin to fade. Something similar happens inside massive stars. For millions of years, fusion reactions generate enormous pressure. This pressure pushes outward against gravity. Eventually, however, the star begins exhausting the materials needed to keep those reactions going. The outward pressure weakens. Gravity notices. And gravity has been waiting very patiently for this moment. The result is one of the most violent events in the universe. A supernova. This is sleepy fact number 8. Many black holes are created after enormous stellar explosions called supernovas. As the star's core loses its ability to resist gravity, collapse begins. And when astronomers say collapse, they mean collapse. The star's central regions plunge inward at incredible speeds. Matter crashes together. Temperatures soar. Shockwaves erupt. and suddenly the entire star explodes outward in a colossal blast. For a brief moment, a dying star can outshine entire galaxies. Imagine every light bulb in every city on Earth turning on at once. Then multiply that brightness by numbers so large they begin to lose meaning. Then keep going. The explosion races across space. Layers of gas are hurled outward. Heavy elements are scattered across the cosmos. Future planets. Future oceans. Future living creatures. Even the atoms that eventually became your body were forged in explosions similar to these, which is a rather poetic thought for something called a supernova, though admittedly less poetic if you're standing too close. Fortunately, you're observing from a safe distance. A very safe distance. The sort of distance measured in light years rather than good intentions. As the expanding cloud slowly drifts away, something remains behind. The star is gone. But the story isn't finished, because the core survives. And what happens next is extraordinary. This brings us to sleepy fact number 9. A black hole forms when a massive stellar core collapses under its own gravity. Without the outward pressure from fusion, gravity becomes the undisputed champion. The remaining core compresses. And compresses. And compresses again. Matter is squeezed into a smaller and smaller volume. Imagine trying to fit an entire mountain into a grain of sand. Then imagine doing that with something much larger than a mountain. The densities involved are almost impossible to picture. A teaspoon of material from certain collapsed stellar remnants could outweigh entire mountains on Earth. And black holes push this compression even further. The core continues collapsing until it forms the object you're now looking at. A black hole. Silent, dark, mysterious. The final stage of a giant star's life. It's strangely peaceful. After all the explosions, all the violence, all the unimaginable energy, the result is stillness. The cosmic equivalent of a dramatic action movie ending with someone quietly turning off the lights. You float nearby, watching starlight bend around the darkness. And it's difficult not to feel a little impressed. A star lived, burned, exploded, collapsed, and transformed into one of the strangest objects in existence. Yet the story of black holes wasn't discovered overnight. In fact, scientists began imagining them long before anyone knew they truly existed. Which brings us to sleepy fact number 10. The idea of black holes existed centuries before modern astronomy confirmed them. As early as the 18th century, some thinkers wondered whether gravity could become so powerful that even light might be trapped. At the time, this sounded more like an interesting thought experiment than a real object. After all, nobody had ever seen anything remotely similar. And the universe was still filled with mysteries. Quite a few mysteries, actually. Astronomers were essentially trying to understand reality while using telescopes that would look suspiciously decorative by modern standards. Then, in the early 20th century, Albert Einstein developed his theory of general relativity. This theory described gravity not as an invisible force pulling objects together, but as the bending of spacetime itself. Soon afterward, physicists realized something remarkable. Einstein's equations seemed to allow for objects so dense that light could not escape. At first, many scientists found the idea difficult to believe, including Einstein himself. The universe, however, did not request anyone's opinion. Over the following decades, observations accumulated. Evidence grew. Theoretical predictions became stronger. And eventually astronomers discovered that black holes weren't merely mathematical curiosities. They were real. The darkness ahead of you is proof. You drift quietly through space once more. Behind you lies the memory of a giant star's final moments. Ahead of you waits the black hole it left behind. A strange cosmic monument built from gravity, time, and the ashes of a vanished sun. The stars continue shining. The galaxies continue turning. And somewhere in the vast darkness, another massive star is already nearing the end of its life, patiently preparing to become the next chapter in the story. For now, though, you simply float, watching, wondering, and slowly discovering that the universe may be far stranger than anyone ever imagined. You've already met a black hole. You've admired its darkness from a respectful distance. You've watched a giant star collapse and transform into one of the strangest objects in the universe. And now you've made a decision that is either incredibly brave or spectacularly unwise. You're going closer. Not too close. At least that's what you're telling yourself. The black hole hangs ahead like a perfectly dark circle cut into the fabric of reality. Around it, distant stars appear bent and distorted. Entire patches of the cosmos seem stretched into strange shapes, as though the universe itself were made of soft glass being gently pressed inward. It's beautiful, terrifying, and strangely peaceful. You drift forward through the silence. There are no warning sirens, no flashing lights, no helpful cosmic tour guide shouting, "Perhaps this is far enough." Just darkness, endless darkness. And somewhere ahead lies one of the most famous boundaries in all of science, the event horizon. This brings us to sleepy fact number 11. The event horizon is the boundary surrounding a black hole where escape becomes impossible. Imagine a waterfall. Far upstream, the river moves slowly. A strong swimmer can easily paddle against the current. Closer to the edge, however, the water begins moving faster and faster. Eventually, there comes a point where no matter how strong you are, the current wins. The event horizon works a little like that. Outside the boundary, objects can still move away from the black hole. Inside it, every possible future leads inward. There are no exits, no shortcuts, no hidden emergency staircases. The universe has essentially installed a one-way door and forgotten to include a return policy. As you float closer, the strange thing is that the boundary itself remains invisible. You can't see a line drawn through space. You won't encounter a giant cosmic fence. There isn't even a sign reading, "Warning, reality gets weird beyond this point," which honestly feels like an oversight. Instead, the event horizon exists as a mathematical boundary, an invisible dividing line separating two very different regions of reality. And yet, if you accidentally crossed it, nothing dramatic would happen immediately. No explosion, no flash, no cosmic alarm clock. You would simply continue falling, which somehow feels even more unsettling. Ahead of you, stars shimmer around the black hole's edge. The distortion becomes stronger. The universe begins looking increasingly less interested in behaving normally. And that brings us to sleepy fact number 12. The event horizon exists because the escape velocity becomes greater than the speed of light. Now, escape velocity sounds complicated, but you've actually encountered it before. Imagine throwing a ball into the air. Gravity pulls it back down. Throw it harder and it rises higher before returning. Throw it even harder and it travels farther still. If you could somehow throw it fast enough, it would escape Earth's gravity entirely. No return trip required. That speed is called escape velocity. Earth's escape velocity is about 11 kilometers per second. The Moon's is much lower. The Sun's is much higher. And a black hole takes the concept to an entirely unreasonable extreme. Near the event horizon, escaping would require moving faster than light itself. Unfortunately, the universe has rules. And one of the biggest rules is that nothing with mass can travel faster than light. Not rockets. Not planets. Not sandwiches. Not even that one sock that disappears every time you do laundry. As far as scientists can tell, light remains the ultimate speed limit. And if light can't escape, neither can anything else. You drift onward. The darkness ahead seems almost calm, patient, like it has all the time in the universe. Which, to be fair, it probably does. As you stare at the black hole, another strange effect becomes impossible to ignore. The stars behind it appear warped, bent, twisted into arcs of light. Some seem stretched into glowing rings. Others appear in places they definitely shouldn't be. This leads us to sleepy fact number 13. Black holes dramatically curve spacetime around them. To understand this, imagine placing a heavy bowling ball on a stretched rubber sheet. The sheet bends downward beneath the weight. Now roll a marble nearby. Instead of moving in a straight line, the marble follows the curve. This analogy isn't perfect, but it helps illustrate a remarkable truth. Gravity isn't simply a force pulling objects together. According to Einstein, gravity is the result of mass bending spacetime itself. And black holes are among the most extreme examples of this phenomenon. Their mass is packed into such a small region that the surrounding geometry of spacetime becomes severely distorted. You aren't merely approaching a heavy object. You're approaching a place where reality itself has been reshaped. A place where straight lines stop behaving like straight lines. A place where the universe folds inward around gravity's overwhelming presence. The effect is so powerful that even light follows the curves. Which brings us directly to sleepy fact number 14. Black holes can bend light through a phenomenon called gravitational lensing. Light normally travels in straight lines. At least it tries to. Near a black hole, however, spacetime itself is curved. As light passes through this distorted region, its path bends along with it. Imagine driving on a perfectly straight road. Then discovering the road itself has been twisted into a giant spiral. You're still following the road. The road simply has other plans. That's essentially what happens to light near a black hole. The result is one of the most beautiful sights in the cosmos. Distant stars become stretched into glowing arcs. Galaxies appear distorted. Sometimes complete rings of light form around massive objects. Astronomers call these Einstein rings, which sounds much more elegant than space doing something deeply confusing again. You watch as distant starlight wraps around the black hole like a luminous halo. The darkness remains perfectly black. Yet around it, light dances and bends in ways that seem impossible. It's like watching reality perform slow-motion magic tricks. Only the magician is gravity. And the audience is everyone who has ever looked up at the night sky. You continue drifting. Closer now. Still outside the event horizon. Still safe. Probably. The stars behind you remain familiar. The stars ahead seem increasingly distorted. And the deeper you look, the stranger everything becomes. Which leads us to sleepy fact number 15. A black hole doesn't simply affect nearby objects. It changes how the entire surrounding region of space appears. Imagine standing in a room filled with mirrors. Every reflection bends and twists unexpectedly. Nothing is quite where it should be. Distances feel strange. Angles seem wrong. Your brain constantly tries to make sense of what it's seeing. The area around a black hole creates a similar effect. Light from distant stars can take curved paths around the object. Some photons may orbit temporarily before escaping. Others circle multiple times. Some never return at all. The result is a view unlike anything else in the universe. Space itself becomes visually distorted. Not because your eyes are failing. Not because your telescope needs cleaning. But because reality has genuinely changed shape. You float quietly in the darkness, watching starlight curve around the invisible giant ahead. The black hole remains silent, patient, unmoving. A perfect shadow surrounded by warped light. And as you observe the strange geometry of the cosmos, you begin to realize something remarkable. You haven't even crossed the event horizon. You haven't fallen in. You haven't reached the truly extreme regions yet. Everything you've seen so far is happening outside the black hole, in the relatively normal neighborhood, which is a slightly alarming definition of normal. Because if this is the universe behaving itself, you can only imagine what waits deeper ahead. For now though, you simply drift, watching galaxies bend, watching starlight curve, and standing at the edge of one of the most extraordinary boundaries nature has ever created. You've spent some time hovering near the edge of a black hole. You've admired the warped starlight. You've learned about the event horizon. You've watched gravity bend reality into shapes that would make a geometry teacher quietly resign and move to the countryside. And now, something even stranger is about to happen. Because black holes don't merely distort space. They distort time. Which is unfortunate. Time already has enough problems. It moves too quickly during vacations. Too slowly during meetings. And somehow manages to disappear entirely when you're trying to remember where you left your keys. Yet near a black hole, time becomes far stranger than any everyday inconvenience. You drift closer. Still safely outside the event horizon. The darkness ahead remains perfectly silent. Stars shimmer in the distance. And somewhere in the depths of spacetime, the universe is preparing to demonstrate one of its most astonishing tricks. This brings us to sleepy fact number 16. Time moves more slowly near a black hole. At first, this sounds impossible. Time is time. A second is a second. A minute is a minute. That's how it works, or at least that's how it feels. But according to Einstein's theory of relativity, time is not as fixed as it appears. The passage of time depends on gravity. The stronger the gravity, the slower time moves. Near Earth, this effect is tiny. Tiny enough that you never notice it while eating breakfast or trying to decide whether that plant on your windowsill is thriving or simply refusing to give up. Near a black hole, however, the effect becomes enormous. The closer you get to the black hole, the more slowly your clock ticks compared to clocks farther away. You glance at your imaginary cosmic wristwatch. It appears normal. Nothing unusual is happening. The seconds continue passing. Your heartbeat remains steady. Everything feels perfectly ordinary. And that's the strange part. You would never notice the difference yourself. Time would feel completely normal to you. It's everyone else who would see something unusual. Which leads us to sleepy fact number 17. Gravitational time dilation is a real phenomenon predicted by Einstein's theory of relativity. Back in 1915, Albert Einstein introduced a revolutionary idea. Space and time weren't separate things. Instead, they formed a single interconnected fabric called spacetime. Massive objects bend this fabric. And when spacetime bends, both space and time are affected. The stronger the gravity, the more dramatic the effect. At the time, the idea sounded almost unbelievable. Many scientists struggled to accept it. The universe, meanwhile, continued behaving exactly as Einstein predicted, which must have been immensely satisfying. Imagine spending years explaining a complicated idea only to discover reality itself has taken your side. That's a good day for a physicist. As you float near the black hole, you're witnessing one of relativity's most extreme consequences. Gravity isn't merely pulling on objects. It's influencing the very rate at which time flows. The black hole isn't just changing where things go. It's changing how quickly the future arrives. And that is deeply strange. Ahead of you, the dark circle hangs motionless. The surrounding stars seem frozen in eternal silence. You continue drifting. And now it's time for sleepy fact number 18. A clock near a black hole can run dramatically slower than a clock far away. Imagine two identical clocks. One remains safely distant from the black hole. The other travels close to the event horizon. Both clocks start at exactly the same moment. Hours pass. Days pass. Perhaps even years. Eventually the clocks are compared. To everyone's surprise, they no longer agree. The clock near the black hole shows less time has passed. Not because it malfunctioned. Not because the batteries died. Not because someone forgot to wind it. The clock genuinely experienced less time. This isn't science fiction. It's a measurable consequence of gravity. In fact, scientists must account for smaller versions of this effect every day. GPS satellites orbiting Earth experience time differently than clocks on the ground. Without corrections based on relativity, navigation systems would quickly become inaccurate. Which means Einstein indirectly helps people find coffee shops. A contribution to humanity that deserves some appreciation. The black hole ahead takes the same effect and amplifies it enormously. The deeper you travel into its gravitational field, the slower your personal timeline becomes compared to the rest of the universe. You imagine spending a few hours near the event horizon. Nothing unusual from your perspective. Then returning home, only to discover decades have passed elsewhere. A rather inconvenient outcome if you've forgotten to pay your electricity bill. Or promise someone you'd be back before dinner. The universe can be surprisingly strict about scheduling. You continue floating through the darkness. The stars remain beautiful. The silence remains complete. And the consequences of gravity grow increasingly difficult to ignore. This brings us to sleepy fact number 19. Extreme gravity changes not only time but also the way observers see one another. Suppose someone far away is watching you approach the black hole. From your perspective, you continue moving normally. Everything feels natural. You drift closer. Closer still. The event horizon approaches. Yet to the distant observer, something extraordinary happens. You appear to slow down. Gradually. Continuously. As though time itself is stretching. Your movements become slower and slower. Your signals take longer to arrive. Your image grows dimmer. Redder. Fainter. To the observer watching from afar, it would seem as though you never quite crossed the event horizon. Instead, you appear frozen near the edge forever. Suspended in time. Like the world's slowest arrival. Imagine spending eternity almost reaching your destination. It's the cosmic equivalent of buffering. Except significantly more scientific. And considerably harder to fix by restarting the router. From your own perspective, however, you continue onward normally. This difference between observers is one of the strangest consequences of relativity. Both viewpoints are valid. Both describe reality. And somehow the universe manages to make them coexist. Physics occasionally feels like it was designed by someone who enjoyed puzzles a little too much. The black hole remains silent. Unbothered. Patient. As if it has witnessed this confusion countless times before. Which brings us to sleepy fact number 20. The closer you get to a black hole, the more extreme these relativistic effects become. Far away, gravity behaves much as you'd expect. Objects fall. Planets orbit. Time differences remain tiny. Life proceeds normally. Closer to a black hole, however, reality begins operating according to rules that challenge everyday intuition. Time slows. Light bends. Distances become strange. The geometry of spacetime twists into forms that feel almost impossible to visualize. And yet every observation astronomers have made suggests these effects are real. The universe genuinely works this way. No special effects required. No hidden tricks. No cosmic stagehands pulling ropes behind the curtain. Just gravity acting according to the laws of nature. You drift quietly in the darkness. The black hole looms ahead. A region where space bends. Where time stretches. Where some of humanity's deepest ideas about reality are put to the test. Far away, stars continue shining. Galaxies continue turning. Civilizations continue measuring the passage of time. Yet here, near one of the most extreme objects in existence, time itself has become part of the story. And as you watch the warped starlight surrounding the darkness, a remarkable thought settles into your mind. The black hole isn't merely an object. It's a laboratory. A place where the universe reveals its deepest secrets. A place where gravity becomes so powerful that even time must obey. For now, though, you remain safely outside the event horizon, floating peacefully, watching the stars, and allowing the slow, ancient rhythm of the cosmos to carry you onward into the next chapter of your journey. You've spent time near the event horizon. You've watched space bend itself into impossible shapes. You've witnessed time slow to a crawl. And now, as you drift a little closer to the black hole, you notice something unexpected. It's bright. Very bright. In fact, it's almost absurdly bright, which feels slightly unfair. After all, this is a black hole. Darkness is supposed to be its entire brand. Yet ahead of you, the darkness is surrounded by one of the most luminous phenomena in the universe. A blazing whirlpool of light. A cosmic traffic jam of superheated gas. A glowing ring spiraling endlessly toward a destination from which nothing returns. You watch it turn. Slowly. Relentlessly. Beautifully. Like a giant celestial drain swirling at the center of existence. Only considerably larger. And significantly less helpful if you've misplaced your car keys. This brings us to sleepy fact number 21. Many black holes are surrounded by structures called accretion disks. An accretion disk forms when gas, dust, and other material become trapped by the black hole's gravity. Rather than falling straight inward, the material begins orbiting. The particles circle faster and faster. They collide. They swirl. They form an enormous rotating disk around the black hole. Imagine water circling a drain. Now replace the water with entire clouds of cosmic gas. Replace the sink with an object capable of swallowing stars. And replace your bathroom with a region several times larger than the solar system. That's roughly the idea. The disk stretches across vast distances, glowing brilliantly against the darkness of space. And unlike the black hole itself, the accretion disk is impossible to ignore. You drift quietly beside it. The swirling material looks almost peaceful. Almost. The reality is considerably more dramatic. Because the gas in the disk isn't simply orbiting. It's fighting. Every particle is competing with every other particle. They rub together, collide together, crash together. And that leads us directly to sleepy fact number 22. The material inside an accretion disk becomes incredibly hot. As gas spirals inward, friction builds. Particles moving at different speeds constantly interact. Energy is released. Temperatures climb, and climb, and climb again. Soon the gas becomes unimaginably hot. Millions of degrees. Sometimes tens of millions of degrees. Hot enough to make the center of a volcano seem refreshingly moderate. Hot enough to make the surface of the sun look like it's having a relatively comfortable afternoon. The disk glows in brilliant colors. White, blue, gold. Streams of plasma twist through the darkness like luminous rivers. The sight is breathtaking. Though admittedly difficult to enjoy for very long without specialized equipment and a strong commitment to not being vaporized. The closer material moves toward the black hole, the faster it travels. And the faster it travels, the hotter it becomes. It's a cosmic cycle of acceleration. A giant whirlpool powered entirely by gravity. Around you, glowing gas races through space. The black hole itself remains silent, dark, motionless. Like the world's least talkative dinner guest. Everything around it is doing the work. Which brings us to sleepy fact number 23. Material in accretion disks can travel at enormous speeds. You watch a glowing stream of gas orbit the black hole. It moves so quickly that your brain struggles to process the scale. Thousands of kilometers per second. Sometimes a significant fraction of the speed of light itself. Entire clouds of matter circle the darkness at velocities that would make the fastest spacecraft ever built look like they're searching for a parking spot. The motion is relentless. Endless. Day and night don't exist here. The disk never closes. Never sleeps. Never takes a holiday. The particles continue their journey inward. Orbit after orbit. Year after year. Millennium after millennium. Some eventually cross the event horizon. Others remain trapped in the disk for astonishing lengths of time. All of them are participating in one of the universe's most spectacular gravitational performances. You continue floating nearby, watching the glowing ring spin through the darkness. And suddenly another realization arrives. This disk isn't merely bright. It's extraordinarily bright. Far brighter than most people would expect. Which brings us to sleepy fact number 24. The region around a feeding black hole can become one of the brightest places in the universe. This surprises many people. After all, black holes themselves emit no light. Yet the material surrounding them can outshine entire galaxies. The secret is energy. As matter falls inward, enormous amounts of gravitational energy are converted into heat and radiation. In some situations, this process releases energy more efficiently than nuclear fusion. The same fusion process that powers stars. Imagine building the brightest lighthouse on Earth. Then building another one. Then another million. Then discovering the black hole still isn't impressed. That's the scale we're dealing with. Some actively feeding black holes produce staggering amounts of light. They can be detected across billions of light years. Their glow travels through the cosmos for millions upon millions of years before finally reaching astronomers' telescopes. And all of it originates from material falling toward a region that emits no light at all. The universe occasionally enjoys irony. This is one of those occasions. You drift quietly through the darkness. The glowing disk illuminates the surrounding space. Faraway stars shimmer beyond the brilliant ring. The black hole remains invisible at the center. A perfect shadow surrounded by fire. And the deeper you observe, the stranger the story becomes. Because not all of this radiation is visible. In fact, much of the most energetic light can't be seen by human eyes at all. Which leads us to sleepy fact number 25. Accretion disks often produce powerful X-rays. As the gas reaches extreme temperatures, it begins emitting high-energy radiation. Among the most important forms are X-rays. These are far more energetic than visible light. Human eyes can't detect them, fortunately. Otherwise, the night sky would occasionally become a much more exciting place than anyone requested. Astronomers use X-rays to study black holes throughout the universe. Even though black holes themselves remain invisible, the hot gas surrounding them shines brightly in X-ray wavelengths. It's one of the ways scientists locate these elusive objects. In a sense, astronomers often find black holes by studying everything around them. Like trying to identify an invisible celebrity by observing the crowd gathered nearby. The glowing gas becomes a clue. The radiation becomes evidence. The surrounding chaos reveals the presence of the unseen giant at the center. You watch the accretion disk continue its endless dance. Streams of plasma circle the darkness. Light bends around the black hole. Heat pours into space. The entire scene feels alive. Not peaceful exactly, but mesmerizing. Like a cosmic campfire fueled by gravity itself. And perhaps that's one of the strangest things about black holes. They are famous for darkness. Yet some of their most fascinating features are brilliantly bright. The black hole remains invisible. But its influence illuminates everything around it. The gas glows. The radiation spreads outward. The universe announces the black hole's presence through a dazzling display of energy. And as you float beside the blazing disk, watching matter spiral toward its final destination, you begin to understand something remarkable. The darkness at the center may be silent, but the journey toward it is anything but. Ahead, the glowing whirlpool continues turning, patiently, endlessly, preparing for the next stage of your descent into one of the most extraordinary regions in the cosmos. You've spent some time admiring the accretion disk. You've watched rivers of superheated gas race around the black hole. You've witnessed some of the brightest regions in the universe surrounding one of the darkest objects in existence. And now, despite every warning nature has generously provided, you're drifting even closer. Not close enough to cross the event horizon. Not yet. But close enough that gravity is beginning to reveal another one of its less welcoming talents. Ahead of you, the black hole remains perfectly silent. No growling. No ominous soundtrack. No giant cosmic sign reading. Turn back while you still have a normal shape, which is unfortunate, because shape is about to become an important topic. You continue drifting forward. The darkness grows larger. The stars behind you become increasingly distorted. And somewhere deep within the black hole's gravitational grip, a strange force begins making itself known. This brings us to sleepy fact number 26. Black holes can stretch objects through a process known as spaghettification. Yes. Scientists genuinely call it spaghettification. After centuries of studying the cosmos, developing advanced mathematics, and unlocking the secrets of spacetime, humanity eventually arrived at a scientific term that sounds suspiciously like something from an Italian restaurant. Yet the name is surprisingly accurate. Imagine holding a piece of spaghetti. Now imagine gravity pulling one end much harder than the other. The result is stretching. Lots of stretching. Near a black hole, the difference in gravitational pull between various parts of an object can become enormous. The end closest to the black hole experiences stronger gravity. The farther end experiences weaker gravity. The object begins stretching. Longer, thinner, less capable of fitting comfortably into standard furniture. You float safely at a distance, grateful to be observing rather than participating. The universe contains many educational experiences. This is one that most travelers prefer to learn about secondhand. The black hole, meanwhile, remains entirely unconcerned. Gravity doesn't hold grudges. It doesn't target individuals. It simply follows the rules. Relentlessly, patiently, and sometimes rather dramatically. This leads us to sleepy fact number 27. Spaghettification is caused by tidal forces. Now, tidal forces might sound familiar. That's because you experience a gentle version of them every day. Earth's oceans rise and fall because of the moon's gravity. The side of Earth closest to the moon experiences a slightly stronger pull than the far side. This difference creates tides. Near a black hole, however, the effect becomes vastly more powerful. Instead of affecting oceans, it affects everything. Rocks, spaceships, stars, anything that wanders too close. The difference in gravitational pull across an object's length becomes so extreme that stretching begins. The closer the object gets, the stronger the tidal forces become. Imagine standing on a trampoline. Now imagine one foot sinking dramatically while the other remains higher up. The surface beneath you would become increasingly distorted. Near a black hole, spacetime itself behaves in a somewhat similar way, only with considerably fewer safety regulations. You continue floating peacefully. The stars remain bright. The accretion disk glows nearby. And gravity quietly continues rewriting the local definition of personal space. Which brings us to sleepy fact number 28. The strength of tidal forces depends on the size of the black hole. This seems surprising at first. Most people assume larger black holes are automatically more dangerous. In some situations, they're actually gentler. At least initially. A small stellar mass black hole can produce intense tidal forces before you even reach the event horizon. The stretching effect becomes severe very quickly. A supermassive black hole behaves differently. Because its event horizon is so much larger, you could potentially cross it before noticing extreme tidal effects. Which is perhaps the least reassuring fun fact imaginable. Imagine being told, "Good news. You probably won't be stretched into spaghetti immediately." The universe occasionally offers comfort in unusual ways. Far ahead, the black hole hangs like a perfect shadow. Massive, ancient, patient. Its gravitational influence extends across enormous distances. Yet the details of that influence depend on its size, its mass, and your location. Every black hole has its own personality. Though admittedly they all share a tendency to make travel arrangements complicated. You drift onward, carefully, respectfully, and preferably with a return ticket. This leads us to sleepy fact number 29. As you approach a black hole, gravity can become dramatically different over surprisingly short distances. Here on Earth, gravity feels fairly uniform. Your head and feet experience nearly identical gravitational pulls. The difference exists, but it's tiny. Near a black hole, the difference can become substantial. Your feet may experience noticeably stronger gravity than your head. Every meter matters. Every kilometer matters. The closer you approach, the more pronounced these differences become. It's one of the reasons black holes are such extraordinary laboratories for physics. Conditions exist here that simply cannot be recreated on Earth. The laws of gravity reveal themselves in their most extreme form. Scientists study these environments because they allow us to test our deepest theories about the universe. How does gravity behave? How does spacetime respond? What happens when matter encounters the strongest gravitational fields known? The answers lie here. In the darkness. Near the edge of the impossible. And while you're safely observing from a comfortable distance, generations of astronomers continue searching for clues hidden within these extraordinary objects. You watch the warped starlight shimmer around the black hole. The accretion disk continues spinning. The darkness remains perfectly black. And somewhere beyond the event horizon lies a region no information can escape from. Which brings us to sleepy fact number 30. What happens deep inside a black hole remains one of the greatest mysteries in science. According to our current understanding, matter that crosses the event horizon continues inward. Eventually, everything appears to converge toward a central region called a singularity. A place where density becomes unimaginably large. A place where our existing theories begin to break down. A place where physics essentially raises its hand and says, "I'm going to need more information." The singularity isn't merely mysterious. It's a sign that our current understanding of nature is incomplete. General relativity describes black holes extraordinarily well. Quantum mechanics describes the microscopic world extraordinarily well. Yet deep inside a black hole, these two great theories seem unable to fully cooperate. Somewhere beyond the event horizon, hidden forever from direct observation, lies a puzzle humanity has not yet solved. Perhaps future physicists will uncover the answer. Perhaps entirely new theories will emerge. Perhaps the true nature of black holes is stranger than anything we've imagined so far. The universe has a habit of exceeding expectations, especially when black holes are involved. You drift quietly through the darkness. The stars continue shining overhead. The glowing accretion disk circles endlessly around the black hole. Space bends. Time slows. Gravity stretches reality itself. And beyond the invisible boundary of the event horizon, mysteries wait in perfect silence. For now, though, you remain safely outside, watching, wondering, and slowly beginning to understand why black holes continue to captivate scientists, dreamers, and curious minds alike. Because the closer we look, the stranger they become. And somehow, the stranger they become, the more beautiful they seem. The darkness ahead remains motionless, patient, ancient, keeping its secrets for another night as your journey through the universe continues. You've spent time near black holes born from dying stars. You've watched matter spiral inward. You've learned about warped light, slowed time, and the universe's deeply concerning willingness to turn things into spaghetti. And now you're about to meet a different kind of black hole entirely. A much bigger one. Actually, bigger might be an understatement. Calling these objects big is a little like calling the Pacific Ocean slightly damp. The black hole ahead of you is no ordinary stellar black hole. It's a giant. A cosmic heavyweight. A gravitational monarch sitting quietly at the center of an entire galaxy. As you drift through the darkness, stars begin appearing in greater numbers. Thousands become millions. Millions become billions. Soon you're surrounded by an enormous spiral galaxy stretching across the cosmos like a glowing celestial pinwheel. Its arms shimmer with stars. Clouds of gas drift between them. Ancient clusters sparkle in the distance. And hidden at the very center lies something extraordinary. This brings us to sleepy fact number 31. Many galaxies contain supermassive black holes at their centers. These aren't the black holes formed from individual stars. They're vastly larger. A typical stellar black hole might contain several times the mass of our Sun. A supermassive black hole can contain millions or even billions of solar masses. Imagine placing millions of suns into a single object. Then imagine somehow making it even more ridiculous. That's the scale we're dealing with. The supermassive black hole ahead sits quietly in the galactic core. It doesn't glow. It doesn't announce its presence. Yet its gravitational influence extends across vast distances. Like an invisible ruler overseeing an empire of stars. The galaxy continues rotating around it. Stars orbit. Gas clouds drift. Entire solar systems follow paths shaped by its immense gravity. And all the while, the black hole remains perfectly silent. The cosmic equivalent of someone commanding a room simply by sitting there. You continue drifting toward the galactic center. The density of stars increases. The sky becomes crowded with light. And you begin noticing that everything seems to revolve around one particular region. Which leads us to sleepy fact number 32. The center of a galaxy is one of the busiest places in the universe. If you've ever seen a quiet countryside road suddenly become a crowded city intersection, you already understand the basic idea. The outer regions of galaxies are relatively spacious. Stars are spread apart. Things feel calm. The galactic center is different. Very different. Stars crowd together. Gas clouds collide. Gravitational forces interact in complex ways. The entire region buzzes with activity. It's the astronomical equivalent of rush hour traffic. Only instead of cars, you're dealing with billions of stars. And instead of angry drivers, you're dealing with gravity. Which, admittedly, can also be quite aggressive. You float through this crowded stellar environment. Light shines from every direction. Ancient stars pass overhead. Some are older than entire civilizations. Others formed long before Earth itself existed. And somewhere at the center of it all sits a black hole so massive that it influences the structure of the entire galaxy. The scale is difficult to comprehend. The galaxy stretches across hundreds of thousands of light years. Yet everything seems connected to the giant lurking at its heart. This brings us to sleepy fact number 33. The supermassive black hole at the center of our own galaxy is called Sagittarius A star. Astronomers usually pronounce it Sagittarius A star. Though fortunately, nobody expects you to spell it while half asleep. This black hole lives at the center of the Milky Way. Your galaxy. The galaxy containing Earth. The galaxy containing every human who has ever lived, every dinosaur that ever stomped around a swamp, and every person who has ever accidentally replied all to an email. Sagittarius A** contains roughly 4 million times the mass of the Sun. 4 million. Yet despite its enormous mass, it occupies a surprisingly compact region. The stars nearest to it orbit at extraordinary speeds. Astronomers have spent decades observing these stellar motions. By tracking their paths, scientists confirmed the presence of an invisible object with immense mass concentrated into a tiny area. The evidence became overwhelming. Something enormous was hiding there. Something dark. Something powerful. Something that strongly suggested the universe had once again decided to be weird. You imagine standing on a planet near the galactic center. The night sky would be astonishing. Stars would fill the heavens in numbers almost impossible to imagine. The darkness between them would shrink. The sky would glow. And somewhere nearby, Sagittarius A** would quietly continue its ancient watch over the Milky Way. You drift onward through the crowded stellar landscape. The galactic center shines around you. The black hole remains invisible, but its presence is undeniable. Which leads us to sleepy fact number 34. Supermassive black holes grow over time. Like many things in the universe, black holes tend to become larger by acquiring more material. Though their methods are admittedly more dramatic than most. Gas falls inward. Dust accumulates. Stars occasionally wander too close. Other black holes can merge with them. Over millions and billions of years, these processes allow supermassive black holes to increase their mass. Slowly, steadily, patiently. They're not in a hurry. The universe rarely is. Imagine leaving a savings account untouched for several billion years. Eventually the numbers become impressive. Supermassive black holes operate on a somewhat similar principle. Except instead of accumulating money, they're accumulating matter. And instead of a bank statement, they occasionally produce enough energy to outshine an entire galaxy. The central giant ahead has spent eons growing. Generation after generation of stars have come and gone around it. Entire civilizations could rise and disappear without the black hole noticing. Its timeline is measured in epochs rather than years. Its story unfolds across cosmic ages. And it's still growing. Which brings us to sleepy fact number 35. Supermassive black holes can actively feed on surrounding material. Not all the time. In fact, many spend long periods relatively quiet. Sagittarius A**, for example, is fairly calm at the moment. At least by black hole standards. Which is reassuring because we're all currently living in the same galaxy. But some supermassive black holes are far more active. When large amounts of gas fall inward, enormous accretion disks form. Radiation pours into space. Jets of energetic particles erupt outward. The galactic center becomes extraordinarily bright. These feeding periods can dramatically affect surrounding regions. The black hole influences nearby gas. Star formation can change. The entire galaxy may respond to activity occurring at its core. It's a remarkable relationship. The galaxy shapes the black hole. The black hole shapes the galaxy. A cosmic partnership stretching across billions of years. You float quietly among the stars. Around you, the galaxy continues turning through the darkness. The central black hole remains hidden. Invisible. Silent. Yet its influence reaches everywhere. The stars know it's there. The gas clouds know it's there. The structure of the galaxy itself bears its imprint. And as you gaze toward the crowded heart of the Milky Way, you begin to understand something remarkable. Black holes aren't merely isolated curiosities scattered through space. Some of them sit at the centers of entire galaxies. Ancient giants shaping the evolution of cosmic cities made of stars. Patiently waiting. Growing. Watching. As the universe slowly unfolds around them. You've now visited the center of a galaxy. You've watched billions of stars orbit an invisible giant. You've met Sagittarius A**, the supermassive black hole quietly residing at the heart of the Milky Way. And naturally, your next question is the same question humans ask about almost everything. Can it get bigger? The answer, unsurprisingly, is yes. Much bigger. The universe has never encountered a limit it wasn't interested in testing. And when it comes to black holes, nature appears to have approached the concept of large and treated it more as a suggestion than a rule. You drift away from the Milky Way. The galaxy slowly shrinks behind you. Its spiral arms fade into the darkness. Ahead, countless other galaxies fill the cosmos. Each one contains billions of stars. Many contain supermassive black holes. And some contain objects so enormous that even astronomers occasionally pause and say, well, that's ridiculous. This brings us to sleepy fact number 36. Some black holes contain billions of times the mass of the Sun. Not millions, billions. Imagine taking our Sun, then gathering a billion more just like it, then somehow compressing all that mass into a single gravitational object. The result would be one of the largest black holes known to exist. The scale is difficult to grasp. 1,000,000 seconds is about 11 days. 1,000,000,000 seconds is more than 30 years. The difference between millions and billions is enormous, and black holes have managed to make that difference feel routine. As you drift through intergalactic space, you begin realizing just how vast the universe truly is. Some black holes are so massive that entire stellar populations seem insignificant beside them. They're not merely large objects. They're gravitational landscapes, regions of reality shaped by staggering amounts of mass. And yet somehow the universe keeps building bigger ones. You continue floating through the darkness. Stars shine faintly in the distance. Galaxies drift past like luminous islands in a cosmic ocean. And somewhere ahead lies one of astronomy's favorite mysteries. How did these giants become so enormous? Which leads us to sleepy fact number 37. The largest black holes likely grew over billions of years. Black holes don't usually start out gigantic. Even supermassive black holes probably began much smaller. Over time they accumulated matter. Gas drifted inward. Stars wandered too close. Other black holes merged with them. The process continued for millions and billions of years. Slowly, patiently, like the world's most determined snowball rolling downhill. Only instead of collecting snow, it collects entire stars. The universe is surprisingly committed to long-term projects. While humans celebrate 5-year plans, black holes casually spend a few billion years working on personal growth. And somehow it pays off. The giants you see today are the result of countless cosmic events layered atop one another across unimaginable spans of time. Generation after generation of stars contributed material. Galaxies collided. Matter accumulated. The black holes grew. The universe kept going. No deadlines. No performance reviews. Just gravity doing what gravity does best. You drift onward. Ahead of you, a distant galaxy shines unusually bright. Its center glows with astonishing intensity, almost as if a cosmic spotlight has been switched on. Which brings us to sleepy fact number 38. Some actively feeding supermassive black holes create objects called quasars. Quasars are among the brightest objects in the known universe. They occur when enormous amounts of matter fall toward a supermassive black hole. The resulting accretion disk becomes incredibly energetic. Radiation pours into space. The entire galactic center lights up. From vast distances, astronomers may not even see the galaxy itself clearly. Instead, they see the brilliant glow of the quasar. Imagine placing a flashlight at the center of a city. Now imagine the flashlight becoming brighter than the entire city. Then brighter than thousands of cities. Then brighter than entire galaxies. You're getting closer to the idea. The quasar ahead radiates immense energy. Its light has traveled billions of years through space. It began its journey long before Earth looked the way it does today. Long before humans existed. Long before anyone stared up at the stars and wondered what was out there. And yet that ancient light is still traveling. Still carrying information across the cosmos. Still telling the story of a hungry black hole from the distant past. You watch the brilliant glow. The black hole itself remains invisible. Naturally, black holes seem committed to letting everything else do the talking. Which leads us to sleepy fact number 39. Quasars helped astronomers discover that supermassive black holes existed. When quasars were first observed, scientists were puzzled. The objects appeared incredibly distant, yet astonishingly bright. Far brighter than ordinary stars. Far brighter than astronomers expected. For years, researchers debated their nature. What could possibly generate so much energy? The answer turned out to be black holes. Specifically, supermassive black holes consuming enormous amounts of material. As matter spiraled inward, gravitational energy transformed into radiation. The process released extraordinary amounts of power. Suddenly, the mystery began making sense. The brightest beacons in the cosmos were often powered by invisible giants. It's one of the universe's favorite tricks. Hide the main character. Let everyone else reveal the plot. Astronomers continue studying quasars today. Each one offers clues about black hole growth, galaxy evolution, and the history of the universe itself. They're cosmic lighthouses illuminating some of the deepest mysteries in science. You continue drifting through the darkness. Galaxies shimmer around you. Ancient light crosses unimaginable distances. And somewhere ahead waits a true record holder. one of the largest black holes ever discovered. Which brings us to sleepy fact number 40. Some black holes are so massive that they challenge our understanding of how black holes grow. Astronomers have discovered giants containing tens of billions of solar masses. Tens of billions. The numbers become so large that they almost stop feeling real. These black holes occupy the centers of enormous galaxies. Their gravitational influence extends across vast regions of space. Their histories stretch back nearly to the beginning of the universe. And yet scientists still aren't entirely sure how some of them became so massive so quickly. The early universe may have produced conditions that allowed rapid growth. Perhaps black holes merged frequently. Perhaps enormous clouds of gas collapsed directly into giant seeds. Perhaps the answer involves processes we don't fully understand yet. The truth remains uncertain. And that's part of what makes astronomy so fascinating. Every answer reveals new questions. Every discovery uncovers another mystery waiting in the darkness. You float quietly among the galaxies. The stars continue shining. Quasars blaze across the cosmos. Ancient black holes sit hidden at the centers of vast stellar empires. Some contain millions of solar masses. Some contain billions. Some challenge the limits of what astronomers thought possible. And through it all, gravity continues shaping the universe. Patiently, relentlessly, across billions of years. As you gaze into the darkness, one final realization settles gently into your mind. The black holes you've encountered so far are not rare exceptions. They're part of a grand cosmic story unfolding across the universe. Some are small, some are large, and some are so enormous that even the galaxies around them seem like supporting characters. The giant ahead remains invisible, silent, ancient, a ruler of stars hidden in plain sight. And somewhere out there, beyond even this colossal object, the universe is undoubtedly preparing something stranger still. You've now traveled from dying stars to supermassive giants. You've watched galaxies orbit invisible rulers. You've seen quasars blaze across the universe like cosmic lighthouses. And just when you thought black holes couldn't possibly become any stranger, the universe quietly clears its throat and says, "Actually, we're just getting started." Because so far we've been talking about black holes as though they simply sit there. Dark, silent, motionless, like giant cosmic bowling balls. But many black holes aren't sitting still at all. They're spinning. And not just spinning a little. Some are rotating at speeds so extreme that they literally drag reality around with them. Which feels like the sort of ability that should require a permit. You drift through the darkness. Ahead of you hangs another black hole. The familiar shadow is there. The warped ring of light is there. The event horizon remains perfectly dark. Yet something feels different, subtle, difficult to describe. Almost as though space itself has become restless. The stars seem slightly distorted. The surrounding universe appears to twist ever so gently. And that's because it is. This brings us to sleepy fact number 41. Many black holes rotate. Astronomers call these rotating black holes, which is admittedly a very direct naming system. But after inventing the word spaghettification, perhaps scientists decided to conserve creativity elsewhere. Black holes inherit rotation from the objects that created them. Remember those massive stars we visited earlier? Stars spin. Galaxies spin. Clouds of gas spin. The universe seems remarkably fond of turning things around. When a spinning star collapses into a black hole, much of that rotational motion remains. In fact, the rotation can become dramatically faster. Imagine an ice skater pulling their arms inward while spinning. As their body becomes more compact, their rotation speeds up. A collapsing star behaves similarly. The result is a black hole rotating at incredible velocities. Some may spin hundreds or even thousands of times per second. You pause to appreciate this fact. Somewhere in the universe exists an object larger than entire solar systems that is spinning faster than a kitchen blender. The cosmos occasionally feels like it enjoys showing off. You continue drifting. The black hole ahead remains silent, but its rotation is quietly changing everything around it. Which leads us to sleepy fact number 42. A rotating black hole twists spacetime itself. Now, by this point in your journey, you've become reasonably comfortable with the idea that spacetime bends. Black holes curve it. Stars curve it. Galaxies curve it. Gravity is essentially the universe's way of rearranging geometry. But rotation introduces something new. Instead of merely bending spacetime, a spinning black hole drags it along. Imagine placing a spoon into a cup of coffee. As the spoon rotates, the liquid begins swirling around it. The coffee isn't choosing to move. It's being carried along by the motion. Something surprisingly similar happens near a rotating black hole. Except instead of coffee, we're talking about spacetime itself. The rotating black hole drags the surrounding fabric of reality. Space becomes twisted. Time becomes affected. The entire region begins participating in the black hole's rotation. It's one of the strangest predictions of Einstein's theory. And remarkably, evidence suggests it's real. You watch the stars shimmer around the darkness. The universe itself seems to flow, slowly, subtly, like an invisible current moving through space. The black hole remains perfectly black. Yet reality around it is quietly spinning. Which brings us to sleepy fact number 43. This effect is known as frame dragging. Frame dragging sounds like something that happens when you're trying to move a heavy couch through a narrow doorway. In physics, however, it refers to the twisting of spacetime caused by rotating mass. Earth actually produces frame dragging. So does the sun. Any rotating object can create the effect. The problem is that most objects aren't massive enough for it to become dramatic. Black holes are. Very dramatic. Near a rapidly rotating black hole, frame dragging becomes extraordinary. The twisting becomes so powerful that objects cannot remain completely stationary relative to the distant universe. Space itself is moving. Reality is rotating. And everything nearby is forced to participate. Imagine standing on a giant moving walkway at an airport. Even if you try standing still, the floor beneath you carries you forward. Near a rotating black hole, spacetime behaves in a somewhat similar way. Only instead of transporting tired travelers toward baggage claim, it's transporting reality itself around a gravitational abyss, which is considerably harder to explain on a boarding pass. You drift quietly through the darkness. The stars continue their ancient dance. The black hole continues spinning. And the deeper you look, the stranger things become. This leads us to sleepy fact number 44. Physicists describe rotating black holes using something called the Kerr solution. Back in 1963, a mathematician named Roy Kerr discovered a remarkable solution to Einstein's equations. Until then, many black hole models assumed the objects weren't rotating. Useful for calculations, less useful for reality, because the universe rarely bothers creating perfectly simple examples. Kerr's solution described what happens when a black hole spins. The result transformed our understanding of black holes. Suddenly, scientists realized that rotating black holes possess unique structures and behaviors. Their geometry becomes more complex. Their surrounding spacetime becomes more dynamic. Their influence extends beyond simple gravity. The equations revealed a richer, stranger universe than anyone expected. And that's saying something. Astronomers had already accepted objects capable of trapping light. Yet somehow black holes still found ways to become more interesting. You glance toward the spinning giant ahead. The darkness remains silent. Yet hidden within that silence lies an astonishing level of complexity. The black hole isn't merely a gravitational trap. It's a rotating engine capable of reshaping the surrounding fabric of spacetime. Which brings us to sleepy fact number 45. Rotating black holes contain a region called the ergosphere. The ergosphere is one of the most unusual places in theoretical physics. It exists outside the event horizon. You could technically enter it and still escape, which already makes it friendlier than several other black hole locations we've discussed. The region forms because frame dragging becomes so powerful that spacetime itself is swept around the black hole. Inside the ergosphere, remaining completely stationary becomes impossible. Reality is moving. And reality isn't accepting requests to stop. Imagine standing in the middle of a giant whirlpool. The current becomes so strong that you're inevitably carried along. The ergosphere functions in a somewhat similar way. Only instead of water, the current consists of spacetime itself. Objects entering this region are forced to rotate with the black hole. The universe effectively says, "You may have travel plans, but we're spinning now." The ergosphere fascinates scientists because it may allow energy to be extracted from a rotating black hole. That's right. Under certain conditions, physicists believe it might be possible to steal a tiny fraction of a black hole's rotational energy. Which sounds exactly like the sort of idea that begins with a Nobel Prize and ends with several extremely complicated diagrams. For now, though, you simply observe. The black hole spins silently in the darkness. The stars continue shining. Space bends. Time stretches. Reality twists. And somewhere within the rotating currents of spacetime, the universe reveals yet another layer of its astonishing complexity. You've traveled far from the simple idea of a dark object in space. Black holes are no longer merely holes. They're engines, laboratories, architects of warped geometry, spinning monuments to gravity's imagination. And as you drift beside the rotating giant, watching spacetime itself swirl around the darkness, you begin to realize something remarkable. The deeper you venture into the world of black holes, the less reality resembles common sense. And somehow, that's exactly what makes it so fascinating. You spend time watching black holes twist spacetime. You've learned that some of them spin so rapidly they drag reality along for the ride. You've floated through the strange currents of the ergosphere and discovered that the universe occasionally treats common sense as a polite suggestion. And yet, despite everything you've learned so far, we've arrived at a question that has puzzled some of the smartest people on Earth for decades. A question so difficult that it sits right at the border between two of humanity's greatest scientific achievements. A question hidden deep within the darkness of black holes. The question is surprisingly simple. What happens to information? You drift quietly through space. The stars around you seem calm tonight. The black hole ahead remains silent, patient, ancient, keeping its secrets as it has for billions of years. And somewhere inside that darkness lies one of the greatest mysteries in modern physics. This brings us to sleepy fact number 46. Black holes create something known as the information paradox. Now, the word information sounds harmless. You probably think of emails, phone numbers, passwords you've forgotten, the location of that one charging cable that somehow vanishes every week. In physics, information means something much deeper. It refers to the complete description of a physical system. The properties of every particle, every interaction, every detail that makes something what it is. According to the laws of quantum mechanics, information cannot simply disappear. It can change form. It can move. It can become difficult to find. But it cannot be destroyed. The universe appears to keep very careful records. Unfortunately, black holes seem determined to challenge that rule. Imagine throwing a book into a black hole. The book crosses the event horizon. Gone. No pages return. No chapters reappear. No helpful summary emerges later. From the outside, the information contained within the book seems lost forever. And that's where the trouble begins. Because physics strongly suggests information shouldn't vanish. Yet black holes appear remarkably good at making things disappear. You continue drifting. The darkness ahead remains perfectly silent. The universe offers no immediate explanation. Which leads us to sleepy fact number 47. Quantum mechanics and black holes don't always cooperate easily. By now, you've encountered Einstein's theory of general relativity several times. It's the theory that explains gravity. It describes planets, stars, galaxies, and black holes with extraordinary accuracy. Then there's quantum mechanics, the theory governing tiny particles, atoms, electrons, photons, the microscopic world. Quantum mechanics is also extraordinarily successful. The problem is that these two theories speak slightly different scientific languages. Most of the time that's manageable. Black holes, however, force them into the same room. And things become awkward. General relativity predicts singularities. Quantum mechanics dislikes singularities. General relativity describes smooth spacetime. Quantum mechanics describes uncertainty and probability. Both theories work beautifully. Yet when scientists try combining them inside black holes, disagreements appear. The universe has essentially handed physicists two instruction manuals that both seem correct. Unfortunately, they don't quite agree with each other. And somewhere deep inside a black hole, the missing pages seem to matter. You float onward through the darkness. Stars shimmer overhead. The black hole continues guarding its secrets. And generations of scientists continue searching for answers. Which brings us to sleepy fact number 48. Physicists have debated the information paradox for decades. Entire careers have been built around this mystery. Books have been written. Conferences organized. Blackboards filled with equations. Coffee consumed in quantities that would concern most physicians. The central question remains remarkably stubborn. If information cannot be destroyed, what happens to the information that falls into a black hole? Some scientists propose that information remains trapped forever. Others suggested it somehow escapes. Still others argued that our understanding of black holes must be incomplete. The debate became one of the most famous problems in theoretical physics. Imagine discovering a locked vault. You know something important is inside. You know the answer matters. But nobody can agree on how the lock works. That's essentially the situation physicists find themselves in. The vault is the black hole. The missing information is the mystery. And the universe has been refusing to provide the combination. You drift quietly through the starlight. The black hole remains as mysterious as ever. Yet another clue is waiting. One that makes the puzzle even stranger. This leads us to sleepy fact number 49. Black holes may not last forever. For much of the 20th century, scientists assumed black holes were eternal. Once formed, they would simply continue existing indefinitely. Then, in the 1970s, physicist Stephen Hawking discovered something remarkable. Quantum effects near a black hole's event horizon suggested that black holes could slowly emit radiation. Today this process is known as Hawking radiation. The details are complex. Fortunately, you're floating through a relaxing cosmic bedtime story rather than preparing for a graduate physics exam. The important idea is simple. Black holes may gradually lose energy. Over unimaginably long periods of time, they may slowly shrink. Eventually they could disappear entirely. This realization transformed the information paradox from an interesting puzzle into a major crisis. Because if a black hole eventually evaporates, what happens to all the information that fell inside it? Where does it go? How does the universe preserve it? The questions became even harder. The mystery became even deeper. And physicists became even more determined. You glance toward the dark circle ahead. It remains perfectly silent. No answers emerge. No cosmic hint appears written across the stars. The black hole simply continues existing, unbothered by humanity's confusion. Which brings us to sleepy fact number 50. Nobody yet knows the complete answer. And that's one of the most exciting facts in science. Sometimes people imagine that scientists already know everything important, that the great mysteries have been solved, that all the major discoveries are behind us. The universe strongly disagrees. Black holes remind us that enormous mysteries still exist. Questions remain unanswered. Fundamental aspects of reality remain uncertain. Somewhere between gravity and quantum mechanics, a deeper understanding is waiting to be discovered. Future scientists may uncover it. New theories may emerge. Entirely new ways of thinking about space, time, and information may appear. The solution could transform our understanding of reality itself. Or it could reveal mysteries stranger than anything we've imagined so far. History suggests the universe enjoys doing exactly that. You drift quietly through the darkness. Around you, stars continue shining. Galaxies continue turning. Black holes continue keeping their secrets. And somewhere, perhaps at this very moment, a physicist is staring at a notebook, a computer screen, or a chalkboard, trying to solve the puzzle you've just encountered. The information paradox remains unsolved. The deepest questions remain open. The story continues. And perhaps that's fitting. Because black holes have never really been about certainty. They are reminders that the universe is larger than our understanding, stranger than our assumptions, more mysterious than our expectations. The darkness ahead remains motionless, silent, ancient, a monument to everything we know, and everything we still have left to learn. And as you float beside it, watching starlight bend around its invisible edge, you can't help but feel a sense of wonder. Not because we have all the answers, but because there are still questions worth asking. You've now traveled through spinning black holes, supermassive giants, and some of the deepest mysteries in modern physics. You've watched stars collapse. You've wandered through galactic centers. You've even spent time thinking about information paradoxes, which is generally not something most people do right before bed. And yet, despite everything you've seen, you may still be wondering something surprisingly simple. Are all black holes the same? After all, when people hear the phrase black hole, they often picture a single type of object. A dark sphere, an event horizon, a one-way trip into the unknown. Case closed. But the universe is rarely that simple. Just as there are different kinds of stars, planets, and galaxies, there are also different kinds of black holes. Some are born from dying stars. Some sit at the centers of galaxies. Some may bridge the gap between the two. Together they form a remarkable cosmic family. A family with very unusual reunion dinners. This brings us to sleepy fact number 51. Astronomers classify black holes into different categories based primarily on their mass. Mass is one of the most important properties a black hole can have. It determines how strong its gravity is, how large its event horizon becomes, how it forms, and how it interacts with the surrounding universe. If black holes were animals, mass would be the feature appearing on every identification guide. Fortunately, black holes are not animals. They require significantly less feeding than a pet hamster. Although admittedly the consequences of overfeeding are somewhat larger. As you drift through space, several black holes appear before you. Each looks similar at first glance. Dark, silent, mysterious. Yet their masses differ enormously. And those differences tell their stories. Which leads us to sleepy fact number 52. The most common known black holes are stellar black holes. These are the black holes we've already encountered several times during our journey. They form when massive stars reach the end of their lives. The star collapses. A supernova erupts. And the remaining core becomes a black hole. Most stellar black holes contain somewhere between a few and several dozen times the mass of the Sun. They are the everyday black holes of the cosmos. Which is a slightly alarming sentence when you think about it. Imagine calling an object capable of trapping light every day. Yet compared to the giants you'll soon meet, stellar black holes are actually among the smaller members of the family. Thousands or perhaps millions may exist within the Milky Way alone. Many wander quietly through the galaxy. Invisible. Undetected. Occasionally revealing themselves through interactions with nearby stars. The galaxy may be far more crowded with black holes than most people realize. Which is comforting only if you find invisible gravitational monsters comforting. You continue drifting onward. The stellar black holes fade into the distance. Ahead, another category awaits. And that brings us to sleepy fact number 53. Scientists have found evidence for intermediate mass black holes. For many years, astronomers faced a puzzle. They knew stellar black holes existed. They knew supermassive black holes existed. But what about the middle ground? Were there black holes larger than stellar ones but smaller than galactic giants? The answer appears to be yes. Intermediate mass black holes seem to occupy this missing range. They're larger than ordinary stellar black holes. Yet far smaller than the supermassive giants found in galactic centers. Think of them as the teenagers of the black hole world. Too large to fit comfortably among the small ones. Too small to join the giants. For decades, evidence remained elusive. Astronomers searched patiently. Eventually, observations began revealing objects that fit the expected mass range. The cosmic family tree suddenly gained a missing branch. And scientists were delighted. Astronomers enjoy solving mysteries. Particularly when the universe leaves clues lying around. You watch as one of these intermediate black holes drifts through a dense star cluster. Quiet. Dark. Almost invisible. A bridge between two very different scales of existence. Which brings us to sleepy fact number 54. Supermassive black holes are the largest confirmed black holes known. You've already met some of these giants. Including Sagittarius A*, the black hole residing at the center of our own galaxy. These enormous objects contain millions or billions of solar masses. Some have grown for billions of years. Others may have formed surprisingly early in cosmic history. Every major galaxy astronomers have carefully studied seems to possess a close relationship with its central black hole. The galaxy evolves. The black hole evolves. The two grow together. It's one of the most remarkable partnerships in the universe. As you float near one of these giants, the scale becomes almost overwhelming. Stars orbit it. Gas clouds respond to it. Entire galactic structures bear its influence. And yet the black hole itself remains hidden. Invisible. Silent. A ruler concealed within its kingdom. The contrast is extraordinary. The largest objects in the black hole family often reveal themselves only through their effects on everything around them. And that leads us to sleepy fact number 55. The size differences between black holes can be astonishing. Imagine lining up members of the black hole family. A small stellar black hole stands at one end, perhaps 10 times the mass of the Sun. Next comes an intermediate black hole, hundreds or thousands of solar masses. Then comes a supermassive giant, millions, billions, possibly tens of billions of solar masses. The range is extraordinary. It's a little like comparing a bicycle, a cargo ship, and an entire continent. All belong to the same broad category, yet their scales are dramatically different. Despite these differences, they share fundamental features. Event horizons, gravity, the ability to trap light, the strange warping of spacetime, the remarkable power to challenge our understanding of reality. You drift quietly among them. Small black holes, large black holes, giants hidden inside galaxies, missing links bridging different scales. Together they form a family unlike anything else in the cosmos. And as you gaze across this extraordinary collection of gravitational wonders, a realization slowly settles into your mind. Black holes are not a single object. They're an entire population. A diverse community scattered throughout the universe. Some born from dying stars. Some ruling galaxies. Some occupying the mysterious middle ground between the two. And beyond them may lie even stranger possibilities. Objects not yet confirmed. Ancient relics from the early universe. Theoretical black holes still waiting to be discovered. But those mysteries belong to the next chapter. For now, you simply float among the known members of the black hole family tree. Watching, wondering, and preparing to venture deeper into the unknown. You've now met the known members of the black hole family. The stellar black holes born from dying stars. The intermediate black holes occupying the cosmic middle ground. The supermassive giants ruling entire galaxies. Together, they form an extraordinary collection of objects. And yet, there is a problem. Some astronomers suspect the family tree may not be complete. There may be relatives we've never met. Ancient black holes older than stars. Older than galaxies. Possibly older than almost everything else in the observable universe. Tonight, you're traveling farther back than ever before. Not merely across space, but across time itself. Back toward the beginning. Back toward the moment when the universe was young. A place where the laws of physics still looked familiar, but where conditions were far stranger than anything we experience today. And that brings us to sleepy fact number 56. Some scientists believe black holes may have formed shortly after the Big Bang. Most black holes form from collapsing stars. That's the story we've followed throughout much of this journey. But stars didn't exist immediately after the Big Bang. For millions of years, the universe contained no stars at all. No galaxies. No planets. No black hole-powered quasars. Just a hot, expanding sea of particles and energy. Yet some physicists have proposed that black holes may have formed during this early era anyway. These hypothetical objects are known as primordial black holes. The word primordial simply means ancient, existing from the very beginning. If they exist, primordial black holes could be among the oldest objects in the universe. Imagine finding a bottle floating in the ocean, then discovering it was launched before the first city was built. Before the first tree grew. Before the first mountain formed. That's roughly the level of antiquity we're discussing. These black holes may have witnessed nearly the entire history of the cosmos. You drift through the darkness. The stars seem more distant now. Ahead lies a vision of the infant universe. A place where reality itself was still settling into its modern form. And somewhere within that ancient chaos, black holes may have been born. Which leads us to sleepy fact number 57. Tiny fluctuations in the early universe may have created primordial black holes. The early universe wasn't perfectly smooth. Tiny variations existed. Some regions contained slightly more matter and energy than others. The differences were incredibly small. Yet over cosmic timescales, small differences can become important. Very important. Imagine baking bread. A tiny air bubble in the dough may seem insignificant. But as the loaf expands, that small imperfection becomes much more noticeable. The early universe behaved similarly. Small fluctuations eventually helped create galaxies, stars, and clusters of galaxies. Some physicists suggest that exceptionally dense regions might have collapsed directly into black holes. No star required. No supernova explosion necessary. Gravity simply took over. A black hole formed. And a new cosmic object entered the universe before the first stars ever shone. It's a remarkable idea. One that continues to inspire scientific investigation. You continue floating through the darkness. The infant universe glows faintly around you. Matter swirls. Energy races in every direction. And hidden within the chaos may have been the seeds of some very unusual black holes. Which brings us to sleepy fact number 58. Primordial black holes could potentially exist in many different sizes. The black holes we've discussed so far usually occupy fairly predictable mass ranges. Stellar black holes come from stars. Supermassive black holes grow over immense spans of time. Primordial black holes might be far more diverse. Some theories suggest they could be extremely small. Others suggest they could be much larger. The exact sizes depend on the conditions present during their formation. Imagine a cosmic factory operating during the universe's earliest moments. The products emerging from the assembly line might vary enormously. Tiny black holes. Larger black holes. Possibly entire populations of objects unlike anything produced today. The challenge is that no one knows for certain whether such a factory ever existed. The evidence remains incomplete. The mystery remains unsolved. And astronomers continue searching. The universe rarely reveals its oldest secrets easily. You drift onward. Galaxies appear once more in the distance. Billions of years have passed during your imaginary journey through cosmic history. Stars begin illuminating the darkness again. And another great mystery enters the story. Which leads us to sleepy fact number 59. Some scientists have wondered whether primordial black holes could help explain dark matter. Dark matter is one of astronomy's most famous mysteries. Galaxies contain more gravity than visible matter alone can explain. Something unseen appears to be contributing additional mass. Scientists call this invisible component dark matter. For decades, researchers have tried to determine what dark matter actually is. Many theories involve undiscovered particles. Others explore entirely new possibilities. One possibility is that some dark matter could consist of primordial black holes. Not enormous ones. Not galaxy-sized monsters. But vast populations of ancient black holes scattered throughout space. The idea is intriguing. If enough primordial black holes existed, they might contribute some of the missing mass astronomers observe. However, observations have placed important limits on this possibility. Certain versions of the idea appear unlikely. Others remain under investigation. The case is not closed. The mystery continues. And dark matter remains one of the universe's most stubborn puzzles. Somewhere among the stars, the answer waits patiently. Much like a black hole. Only with slightly fewer event horizons. You continue drifting. The galaxies shimmer around you. The darkness remains calm. The cosmos feels ancient tonight, as though it remembers events that occurred long before stars ever existed. And that brings us to sleepy fact number 60. The oldest black holes may still be hiding somewhere in the universe today. If primordial black holes exist, some could potentially survive to the present day. For billions of years they would have wandered through space. Silent. Invisible. Ancient beyond comprehension. Entire galaxies would form around them. Stars would ignite and die. Planets would emerge. Civilizations would rise. And the primordial black holes would continue their lonely journeys through the cosmos. They would be relics from an era almost impossible to imagine. Objects carrying information from the universe's earliest moments. Living fossils of cosmic history. Astronomers continue searching for signs of their existence. Perhaps future observations will reveal them. Perhaps new telescopes will uncover evidence. Or perhaps nature chose a different path entirely. For now, nobody knows. And that's what makes the story so fascinating. You float quietly among the stars. Around you stretches a universe nearly 14 billion years old. Galaxies spin. Black holes grow. Light travels endlessly through the darkness. And somewhere out there may drift objects born before the first star ever shone. Ancient survivors from the dawn of time. Hidden relics from the universe's earliest chapter. Perhaps they're waiting to be discovered. Perhaps they're merely beautiful ideas. Either way, they remind us of something extraordinary. The deeper we explore the universe, the closer we come to its beginning. And the closer we come to its beginning, the more mysterious everything becomes. The stars continue shining. The galaxies continue turning. And somewhere in the darkness, the oldest black hole in existence may still be quietly waiting for someone to find it. For most of human history, black holes existed only as ideas. Interesting ideas. Brilliant ideas. Sometimes frustrating ideas. But ideas nonetheless. Astronomers could calculate them. Physicists could describe them. Scientists could observe their effects on nearby stars. Yet nobody had ever actually seen one. Which was understandable. Trying to photograph a black hole is a little like trying to photograph darkness itself. Not the darkness in a room. Not the darkness of a cloudy night. The deepest darkness imaginable. An object that allows no light to escape. And yet, against all expectations, humanity eventually succeeded. Tonight, you're traveling not to a distant galaxy or the beginning of the universe. Instead, you're visiting one of the greatest scientific achievements of the modern age. The moment when humanity finally captured an image of a black hole. Or at least something very close to one. You drift through the darkness. Ahead, scientists are waiting. Observatories stand on mountaintops. Radio dishes point toward the sky. Computers process astonishing amounts of information. Thousands of people are working together. All focused on a single goal. To photograph the unphotographable. And that brings us to sleepy fact number 61. The first image of a black hole was released in 2019. On April 10, 2019, scientists revealed an image that immediately became famous around the world. You may have seen it before. A glowing orange ring surrounding a dark center. Simple, blurry, and absolutely revolutionary. For decades, black holes had existed primarily through indirect evidence. Astronomers observed stars orbiting invisible objects. They studied X-rays from accretion disks. They measured gravitational effects. The evidence was overwhelming. Yet this was different. For the first time, humanity could actually look at the region surrounding a black hole. The image spread across newspapers, television broadcasts, websites, and social media. People everywhere stared at the same glowing ring. A picture of something once considered impossible to observe. Not bad for a species that spent much of its history trying to figure out where lightning came from. You continue drifting. The image hangs before you. Familiar now. Historic. a blurry ring that changed astronomy forever. Which leads us to sleepy fact number 62. The photographed black hole is located in a galaxy called Messier 87, usually shortened to M87. This giant galaxy lies approximately 55 million light-years from Earth. That's an astonishing distance. The light captured in the famous image began its journey long before humans invented agriculture, long before pyramids, long before cities, long before recorded history. The photons traveled through intergalactic space for millions of years, crossing unimaginable distances, eventually arriving on Earth, where scientists used them to create one of the most famous images in modern science. The black hole itself is enormous, absolutely enormous. Its mass is estimated at roughly 6.5 billion times the mass of the Sun. 6.5 billion. If Sagittarius A** is impressive, M87's black hole enters the room and quietly wins the competition without saying a word. Its event horizon is larger than our entire solar system. The scale is almost impossible to visualize. And yet, despite its immense size, it appears tiny from Earth because it is so far away. Like trying to photograph a grapefruit sitting on the moon. The challenge was extraordinary. Which brings us to sleepy fact number 63. The image was created using a network of telescopes spread across Earth. No single telescope is powerful enough to directly photograph a black hole from such distances. Astronomers needed something larger, much larger. So they came up with an ingenious solution. Instead of building one gigantic telescope, they linked together observatories around the world. Telescopes in Chile, Hawaii, Mexico, Spain, Antarctica, Arizona, several other locations. Together they formed a project known as the Event Horizon Telescope. The idea was remarkable. Combine observations from multiple locations to create the equivalent of a telescope nearly the size of Earth itself. It's one of those scientific solutions that sounds almost impossible, then somehow works. Imagine needing a larger camera. So instead of buying one, you coordinate observatories scattered across an entire planet. Astronomy occasionally approaches problems with admirable ambition. You watch radio dishes turning toward the sky. Each telescope gathers information. Each contributes a piece of the puzzle. Thousands of hours of work combine into a single image, a portrait of darkness. Which leads us to sleepy fact number 64. Creating the image required enormous amounts of data. The Event Horizon Telescope generated so much information that sending it over the internet wasn't practical. Instead, scientists stored the data on physical hard drives. Lots of them. Hundreds of them. The total volume reached several petabytes. That's millions of gigabytes. Enough data to make your laptop immediately reconsider its life choices. The hard drives were physically transported to specialized facilities where the information could be processed. Teams of researchers spent months analyzing the observations. Computers combined signals from telescopes separated by thousands of kilometers. Gradually a picture emerged. Not instantly. Not dramatically. Science rarely works that way. Instead, the image appeared through careful analysis, verification, and collaboration. Thousands of people contributed to the final result. Astronomers, engineers, computer scientists, mathematicians, technicians, researchers from around the world. It's a reminder that some of humanity's greatest discoveries happen when enormous groups of people work together. The black hole may be solitary. The effort required to observe it was anything but. You continue drifting. The famous image glows ahead. A ring of light surrounding darkness. Simple, elegant, historic, and it carries one final lesson. Which brings us to sleepy fact number 65. The famous image is actually a picture of the black hole's shadow, not the black hole itself. Remember, black holes emit no light. The dark region visible in the image isn't the event horizon directly. Instead, it's the shadow created by the black hole's immense gravity. Light from the surrounding accretion disk bends around the black hole. Some of that light reaches us. Some falls inward forever. The result is a dark central region surrounded by glowing material. The shadow reveals the black hole's presence, its size, its influence, its extraordinary power. In a sense, humanity didn't photograph the black hole itself. It photographed the effect the black hole has on nearby light. Like seeing the outline of an invisible object because of the way it blocks a bright background. The darkness reveals itself through contrast. The unseen becomes visible. And that may be one of the most beautiful ideas in all of astronomy. Sometimes we learn about something not by observing it directly, but by observing how it changes the world around it. You float quietly beside the historic image. The stars shine softly in the distance. The glowing ring surrounds its dark center. A monument to human curiosity. A triumph of science and engineering. For centuries, black holes existed only in equations and imagination. Then humanity built a telescope the size of a planet, looked across 55 million light-years of space, and finally captured a glimpse of one. The darkness remains silent. The shadow remains motionless. Yet within that simple image lies one of the greatest achievements in the history of astronomy. Proof that even the most mysterious objects in the universe can eventually reveal themselves, if we're patient enough to keep looking. For most of history, humanity explored the universe using light. Visible light, radio waves, infrared radiation, X-rays. Every great astronomical discovery depended on some form of light reaching our telescopes. We looked, we observed, we photographed, and gradually we learned how the universe works. But imagine trying to understand Earth using only your eyes. You could see oceans, mountains, clouds, cities, yet you would miss something important. You wouldn't hear the crashing waves, the songs of birds, the rumble of thunder, the sound of the world itself. For centuries, astronomers faced a similar limitation. They could see the universe, but they couldn't hear it. Then, in 2015, everything changed. The universe made a sound, and humanity finally listened. This brings us to sleepy fact number 66. Scientists detected gravitational waves for the first time in 2015. The discovery was one of the most important scientific achievements of the 21st century. For nearly 100 years, gravitational waves had existed only as a prediction. Back in 1916, Albert Einstein's theory of general relativity suggested they should exist. Ripples in spacetime itself. Waves traveling through the fabric of the universe. A remarkable idea. But there was a problem. The waves were expected to be extraordinarily tiny. So tiny that detecting them seemed almost impossible. For decades, scientists searched. Technology improved. Experiments became more sophisticated. Still nothing. Then, on September 14, 2015, a signal arrived. Brief, faint, extraordinary. The universe had finally spoken. And it sounded remarkably like two black holes crashing into one another. You drift quietly through the darkness. Far ahead, two black holes orbit each other. Slowly at first, then faster. And faster still. A cosmic dance billions of years in the making. Which leads us to sleepy fact number 67. Black holes can merge together. When two black holes orbit one another, gravity gradually alters their motion. They lose energy. Their orbits shrink. The distance between them decreases. Over immense spans of time, the two objects spiral inward. Closer, closer, closer still. Eventually they collide. The word collide almost feels inadequate. These aren't ordinary objects. Each may contain dozens of solar masses. Their gravitational fields distort spacetime itself. When they merge, the event becomes one of the most energetic phenomena in the universe. Yet from a distance there is no explosion of light. No giant fireball. No dramatic flash visible across the cosmos. Instead, something stranger happens. The collision creates waves. Not waves in water. Not waves in air. Waves in spacetime itself. Reality ripples outward. The fabric of the universe briefly trembles. And those ripples continue traveling through space for billions of years. Until they eventually reach Earth. You continue floating nearby. The two black holes circle faster and faster. Their motion becomes almost dizzying. The dance is reaching its conclusion. And that brings us to sleepy fact number 68. Gravitational waves are ripples in spacetime. Imagine dropping a pebble into a still pond. Ripples spread outward across the water. Now replace the pond with spacetime. Replace the pebble with two merging black holes. The basic idea remains surprisingly similar. Massive accelerating objects create disturbances. Those disturbances travel outward. The waves carry information about the event that created them. As gravitational waves pass through space, they slightly stretch and compress distances. Not by much. In fact, the changes are astonishingly small. Far smaller than an atom. Far smaller than a proton. Yet they are real. The universe itself expands and contracts ever so slightly as the waves pass through. It's almost impossible to imagine. Space is not merely the stage where events occur. Space participates in the performance. Reality itself vibrates. The cosmos becomes an instrument. And black holes provide some of the loudest notes. You watch the ripples spread outward. Across star systems. Across galaxies. Across unimaginable distances. A message traveling through the universe. and eventually reaching a small blue planet orbiting an ordinary star. Which leads us to sleepy fact number 69. The first detected gravitational waves came from two merging black holes. The event occurred approximately 1.3 billion light-years away. Long before complex life appeared on Earth, the collision had already happened. The waves began their journey through space, crossing galaxy clusters, passing stars, traversing cosmic voids, traveling endlessly through the darkness. Eventually they arrived at Earth. Scientists operating the Laser Interferometer Gravitational Wave Observatory, better known as LIGO, recorded the signal. The pattern matched theoretical predictions almost perfectly. Two black holes, one about 36 times the Sun's mass, the other about 29 times the Sun's mass, spiraling together, merging, becoming a single larger black hole. The signal lasted only a fraction of a second. Yet within that brief moment lay a century of scientific history. Einstein's prediction had been confirmed. Humanity had opened an entirely new way of observing the universe. Astronomy gained a new sense. Not sight, not touch, not hearing in the traditional sense, but something close. A way to detect cosmic vibrations traveling through spacetime itself. You drift onward. The merged black hole now spins quietly in the darkness, its violent birth already fading into history. But the waves continue spreading, forever carrying news of the collision across the cosmos. Which brings us to sleepy fact number 70. Gravitational wave astronomy allows us to study black holes in entirely new ways. Before gravitational waves, astronomers usually studied black holes indirectly. They observed nearby stars. They measured X-rays from accretion disks. They photographed shadows. All valuable techniques. All powerful tools. But gravitational waves reveal something different. They allow scientists to observe black holes directly through their motion. Researchers can calculate masses, measure spins, study mergers, test Einstein's theories under extreme conditions. Events that produce little or no light suddenly become observable. It's as though humanity spent centuries watching silent movies, then unexpectedly discovered sound. A completely new source of information became available, a new way to explore reality, and the discoveries are only beginning. You float quietly among the stars. Around you, black holes continue orbiting. Some are destined to merge millions of years from now. Others already have. Their gravitational waves are crossing the universe at this very moment. Ancient messages traveling through spacetime, waiting to be detected, waiting to tell their stories. The darkness remains calm. The stars continue shining. Yet beneath the stillness, the universe is alive with motion. Black holes collide. Spacetime ripples. Reality vibrates. And somewhere on Earth, scientists continue listening. Listening to the echoes of ancient mergers. Listening to the sound of gravity itself. Listening to a universe that, after billions of years of silence, finally revealed that it has been singing all along. You've spent the night exploring some of the strangest objects in existence. You've watched stars collapse. You've drifted through accretion disks. You've witnessed black holes collide and listened to the ripples they sent across spacetime. And now a question naturally appears. A very human question. A question that has probably occurred to almost everyone who has ever looked up at the stars and wondered what might be out there. Could we ever visit one? Not just observe it, not photograph it, not detect it with telescopes. Actually go there. Pack a spacecraft, point it toward a black hole, and begin the journey. As you drift quietly through the darkness, the idea feels both exciting and slightly alarming. After all, humanity has a long history of exploring dangerous places. We crossed oceans, climbed mountains, visited the moon, sent spacecraft beyond the edge of the solar system. When confronted with something mysterious, humans tend to react by attempting to go there. Black holes would probably receive the same treatment. Eventually, assuming someone can find enough volunteers. And that brings us to sleepy fact number 71. A journey to the nearest known black hole would take an incredibly long time. Black holes are not conveniently located, at least not from a travel planning perspective. The nearest known stellar mass black hole currently identified by astronomers lies roughly 1,500 light-years away. That's relatively close by galactic standards. It's also unimaginably far by human standards. Light itself requires 1,500 years to make the journey. Modern spacecraft would require vastly longer. Voyager 1, one of the fastest probes humanity has ever launched, would need tens of millions of years. By the time it arrived, continents on Earth might look different. Languages would have evolved. Entire civilizations could rise and fall. The black hole, meanwhile, would still be waiting, patiently, Black holes are remarkably good at patience. You continue drifting through the stars. The nearest black hole remains far beyond reach, for now. But distance isn't the only challenge. Even reaching one would raise another problem. What exactly would happen when you got there? Which leads us to sleepy fact number 72. A spacecraft could safely orbit a black hole from a sufficient distance. This surprises many people. Black holes are dangerous. No argument there. But they're not magical vacuum cleaners. They don't automatically swallow everything nearby. Gravity depends on distance. Far enough away, a black hole behaves much like any other object with the same mass. Imagine replacing the Sun with a black hole of identical mass. Earth would continue orbiting. The planets would continue following their paths. The solar system would remain gravitationally stable, though admittedly much darker. Plants would likely file formal complaints. The important point is that orbiting a black hole isn't inherently impossible. Given the right distance, a spacecraft could circle one safely. Astronauts might study the accretion disk, measure gravitational effects, observe warped starlight. The view would be extraordinary, though the travel brochure would require some careful wording. You float beside an imaginary spacecraft. Its instruments collect data. The black hole hangs ahead like a dark jewel surrounded by distorted stars. Beautiful, mysterious, and surprisingly approachable from a safe distance, at least compared to actually falling in. Which brings us to sleepy fact number 73. The environment around many black holes would be extremely hazardous. While the black hole itself may remain dark, the surrounding region often becomes extraordinarily active. Accretion disks produce intense radiation. X-rays flood into space. Jets of energetic particles can extend for thousands of light years. Temperatures reach millions of degrees. It's not exactly a relaxing holiday destination. Imagine planning a beach vacation, then discovering the beach emits lethal radiation and occasionally launches streams of plasma at nearly the speed of light. Most travelers would probably reconsider. Any spacecraft approaching an active black hole would require exceptional protection, shielding, distance, careful navigation, and perhaps a strongly worded safety manual. Nature doesn't always make exploration easy. The most fascinating places often come with the longest list of warnings. You continue drifting through the darkness. The accretion disk glows brilliantly nearby. The black hole remains silent. The environment remains spectacularly unfriendly. And yet humans would probably still want to visit, because curiosity has always been difficult to discourage. Which leads us to sleepy fact number 74. Supermassive black holes might actually be safer to approach than smaller ones. This sounds backwards. The larger the black hole, the safer it becomes? In certain situations, yes. Remember the tidal forces responsible for spaghettification. Near small black holes, those forces become extreme very quickly. Near supermassive black holes, the event horizon is vastly larger. The gravitational differences across a person's body can be much smaller at the horizon itself. In theory, an astronaut approaching a supermassive black hole might cross the event horizon without immediately noticing dramatic tidal effects, which is both fascinating and mildly unsettling. Imagine crossing one of the most famous boundaries in the universe and thinking, well, this seems surprisingly normal. Of course, the deeper journey would eventually become much less normal, but the initial experience might be unexpectedly gentle, at least by black hole standards, which remains one of the least comforting categories of reassurance ever invented. You drift onward. The giant black hole ahead appears calm, almost peaceful, its enormous size softening some of the violent effects that smaller black holes produce. And that brings us to sleepy fact number 75. Even if humans never visit a black hole directly, we can still learn an enormous amount about them. This may be the most important lesson of all. Science doesn't always require physical travel. Astronomers study stars they will never reach, galaxies they will never visit, phenomena occurring billions of light years away. Knowledge travels even when people cannot. Every telescope becomes a vehicle. Every observation becomes a journey. Every measurement carries us a little farther into the universe. Black holes are a perfect example. We've photographed them, measured them, listened to them through gravitational waves, mapped their influence on surrounding stars, tested Einstein's theories using their behavior. And we're only beginning. Future observatories will reveal even more. More images, more mergers, more discoveries, more surprises. The universe is extraordinarily generous with mysteries, and black holes continue providing some of the best ones. You float quietly among the stars. The darkness stretches endlessly around you. Far ahead, black holes wait in silence. Ancient, patient, almost certainly unconcerned with humanity's travel ambitions. Perhaps one day our descendants will visit them. Perhaps advanced civilizations will orbit them, study them, even use them in ways we cannot yet imagine. Or perhaps black holes will remain destinations explored only through telescopes and mathematics. Either way, the journey continues. Because exploration isn't defined by distance traveled. It's defined by curiosity. And curiosity has already carried humanity farther than anyone once thought possible. The stars continue shining. The black holes continue waiting. And somewhere in the future, another generation will undoubtedly look into the darkness and ask the same question we've asked tonight. What happens if we go a little closer? You've spent the night exploring black holes as mysteries, as dangers, as cosmic laboratories where the laws of physics reveal some of their deepest secrets. But now it's time to look at them from a different perspective. Not as obstacles, not as monsters, not even as scientific curiosities, but as resources. Because whenever humans discover something powerful, we eventually ask the same question. Can we use it? We've done this with rivers, with wind, with coal, with oil, with sunlight, even with the atom itself. So it was probably inevitable that someone would eventually look at a black hole and think, I wonder if that could power my civilization. The answer is surprisingly interesting and slightly terrifying. You drift quietly through space. Ahead of you hangs a rotating black hole. Dark, silent, patient. Around it, a glowing accretion disk shines brightly against the darkness. Streams of radiation pour outward. Immense amounts of energy move through the surrounding region. And suddenly the black hole begins looking less like a destination, and more like a power plant. This brings us to sleepy fact number 76. Black holes are among the most efficient energy sources known to physics. When matter falls toward a black hole, enormous amounts of gravitational energy are released. You've already seen this process inside accretion disks. Gas spirals inward. Friction increases. Temperatures rise. Radiation pours into space. The remarkable part is how efficient the process can be. A typical nuclear power plant converts only a tiny fraction of matter into usable energy. Even stars like the Sun convert only a small percentage of their fuel through fusion. A black hole can do far better. In some cases, the energy released by material falling toward a black hole can exceed 10% of the matter's total mass energy. For rotating black holes, the efficiency may be even higher. The numbers are astonishing. Imagine throwing a single object into a machine and receiving an enormous burst of energy in return. Nature has effectively created one of the most powerful energy conversion systems in the universe. Not intentionally, of course. Black holes don't accept utility contracts. But the physics is there, waiting. You continue drifting beside the glowing accretion disk. The light surrounding the black hole shines brilliantly. The energy output is staggering. And somewhere, a futuristic engineer is becoming very excited. Which leads us to sleepy fact number 77. An advanced civilization might theoretically build structures around a black hole. This idea belongs to the realm of speculation. But it's scientifically fascinating. Imagine a civilization millions of years more advanced than our own. A civilization capable of engineering projects on astronomical scales. Instead of building power plants around rivers or oceans, they might construct enormous facilities around black holes. The surrounding accretion disk could provide tremendous amounts of energy. Radiation could be captured. Power could be harvested. The black hole would become the centerpiece of an entire technological infrastructure. Science fiction writers have loved this idea for decades. And understandably so. A black hole-powered civilization sounds dramatically more impressive than arguing over electricity bills. The engineering challenges would be immense. The distances enormous. The risks substantial. Yet the laws of physics do not immediately forbid the concept. Which is often enough to keep scientists interested. You watch the black hole glow against the darkness. The idea no longer feels entirely impossible. Just extraordinarily ambitious. Which brings us to sleepy fact number 78. Rotating black holes may contain extractable energy. Earlier in our journey you visited the ergosphere. That strange region outside a rotating black hole where spacetime itself is dragged around by the object's spin. Physicists discovered something remarkable about this region. In theory, it may be possible to extract some of the black hole's rotational energy. The idea was proposed by physicist Roger Penrose in 1969. Today it's known as the Penrose process. The details are wonderfully complicated. Fortunately, Bedtime is not the ideal moment for advanced mathematical derivations. The basic concept is simple. A rotating black hole stores enormous amounts of energy in its spin. Under specific circumstances, some of that energy might be removed. The black hole would continue existing, but its rotation would slow slightly. Imagine borrowing a tiny amount of energy from a spinning flywheel. Except the flywheel contains the mass of millions of suns. The amount of available energy could be extraordinary. Nature occasionally creates batteries on truly ridiculous scales. You continue floating through the darkness. The spinning black hole turns silently before you. A giant reservoir of rotational energy hidden within a gravitational abyss. The universe never seems to run out of surprises. Which leads us to sleepy fact number 79. Some scientists have explored whether black holes could be used for future space travel. Now we're venturing into highly speculative territory. The sort of territory where theoretical physicists become unusually enthusiastic. Several ideas have been proposed. One concept involves using radiation emitted by extremely small black holes as propulsion. Another explores harnessing energy from black holes to power interstellar spacecraft. Some theories even imagine advanced civilizations creating artificial black holes for technological purposes. At present, these ideas remain far beyond human capabilities. Far beyond. The engineering challenges alone are enough to inspire several immediate naps. Yet they demonstrate something remarkable. Black holes are not merely destructive objects. They're also sources of possibility. The more scientists study them, the more potential applications emerge. Most remain theoretical. Some may prove impossible. Others might become relevant to civilizations far more advanced than ours. The future has a habit of surprising people. Just ask anyone from the year 1820 about smartphones. You drift onward. The stars shimmer around you. The black hole continues spinning. And one final thought begins to emerge. Which brings us to sleepy fact number 80. Black holes remind us that the universe contains resources beyond anything humanity currently uses. For most of human history, our energy sources came from Earth. Coal, wind, water. Eventually, sunlight and nuclear reactions. Each step expanded our capabilities. Each revealed new possibilities. Black holes represent another level entirely. Not because humanity will necessarily use them, but because they demonstrate how much energy exists throughout the cosmos. The universe is vast beyond comprehension. Its resources are equally vast. Black holes are among the most dramatic examples. Objects capable of shaping galaxies, bending spacetime, powering quasars brighter than entire stellar systems. The sheer scale is humbling and inspiring. You float quietly beside the spinning giant. The accretion disk glows softly around it. Ancient stars shine in the distance. The darkness remains perfectly calm. For centuries, black holes were viewed primarily as cosmic traps. Places where things disappeared. Regions to be feared. Today, scientists see something more. Mysteries to solve. Laboratories to explore. Potential sources of insight into the deepest workings of reality. Perhaps one day, far in the future, civilizations will use black holes in ways we can barely imagine. Or perhaps they will remain magnificent natural phenomena. Either way, their existence expands our understanding of what's possible. The black hole turns silently. The stars continue shining. And somewhere in the distant future, an engineer may look into the darkness and see not an ending, but an opportunity. You've spent the night exploring black holes from nearly every angle imaginable. You've watched stars collapse into them. You've visited supermassive giants at the centers of galaxies. You've listened to the echoes of black hole collisions and wondered whether future civilizations might one day harness their power. By now, you might feel that black holes can no longer surprise you. The universe would like to respectfully disagree. Because even after decades of research, black holes continue producing facts so strange that they sound less like science and more like something invented during a particularly imaginative dream. And the remarkable part is that these facts are real. Or at least as real as anything involving warped spacetime, invisible singularities, and objects capable of trapping light. Tonight, you're entering a gallery of black hole oddities. A collection of some of the strangest discoveries ever made. The sort of facts that make astronomers stare thoughtfully at a whiteboard for several minutes before quietly adding another equation. You drift through the darkness. Stars shine softly around you. Ahead, a series of black holes waits, each one holding a different surprise. And that brings us to sleepy fact number 81. Black holes can grow larger by eating other black holes. This sounds obvious. After all, black holes consume matter. Why not each other? Yet the reality remains wonderfully strange. Imagine two black holes orbiting one another. Closer, closer, closer still. Eventually they merge. The result is a single larger black hole. Nature essentially combines two of the most extreme objects in existence and somehow creates an even more extreme object. It's the cosmic equivalent of two storms merging into a superstorm. Except the storm bends spacetime and occasionally generates gravitational waves. Astronomers have observed these mergers through gravitational wave detectors. Each detection tells the story of black holes growing larger through collision. Across billions of years, countless mergers may have helped build the enormous black holes we see today. The universe has many construction methods. This is certainly one of the more dramatic options. You continue drifting. The merged black hole spins quietly in the distance. Its history written into the fabric of spacetime itself. Which leads us to sleepy fact number 82. Some black holes move through space at astonishing speeds. It's easy to imagine black holes sitting motionless, patiently waiting, brooding dramatically. But many are moving, very quickly. When massive stars explode as supernovae, the explosions are not always perfectly symmetrical. Sometimes more material is blasted in one direction than another. The result can act like a cosmic kick. The newly formed black hole receives momentum and shoots through space. Astronomers have discovered black holes traveling hundreds of thousands of kilometers per hour. Entire solar systems orbit peacefully. Meanwhile, somewhere in the galaxy, a black hole is effectively speeding down the cosmic highway. Not that space contains speed limits, or traffic signs, or roadside diners. Though perhaps that's for the best. You watch one of these wandering black holes pass silently between the stars. Invisible. Fast. Ancient. A traveler crossing the galaxy alone. Which brings us to sleepy fact number 83. There may be millions of black holes in the Milky Way. When most people think of black holes, they imagine rare objects, exceptional discoveries, unusual cosmic phenomena. In reality, black holes may be surprisingly common. Astronomers estimate that millions of stellar black holes could exist within our galaxy alone. Most remain undetected, not because they're particularly good at hiding, although they are. Rather, because black holes are difficult to observe when they're not actively interacting with nearby matter. Many wander silently through the Milky Way, invisible against the darkness. Imagine walking through a forest at night knowing that millions of invisible objects are scattered throughout it. Fortunately, the galaxy is extremely large. Extremely. The average distances between black holes remain enormous. You're unlikely to accidentally stumble into one during your evening walk. Unless your evening walk becomes unusually ambitious. You continue floating through the galaxy. The stars seem endless, and hidden among them are countless unseen black holes. A population larger than most people realize. Which leads us to sleepy fact number 84. Some black holes launch jets longer than entire galaxies. This is one of the most spectacular sights in astronomy. Certain supermassive black holes produce enormous jets of particles moving at speeds close to that of light. The jets emerge from regions near the black hole and shoot outward into space. For thousands, sometimes even millions, of light years. Imagine a beam extending beyond the width of an entire galaxy. Now remember that the beam originates near a black hole. The scale becomes almost impossible to grasp. The exact mechanisms remain an active area of research. Magnetic fields appear to play a major role. Rotation contributes as well. Whatever the details, the result is extraordinary. The black hole doesn't merely influence its immediate surroundings. It affects vast regions of intergalactic space. A single object helping shape environments across cosmic distances. You watch one of these jets stretch into the darkness. A luminous river flowing through the universe, powered by an invisible engine. And somehow the black hole itself remains hidden. Which brings us to sleepy fact number 85. Black holes have repeatedly surprised scientists. This may be the most consistent black hole behavior of all. Every generation of researchers believes it understands them a little better. Then black holes reveal something unexpected. The first surprise was that they might exist at all. Then came stellar black holes, supermassive black holes, gravitational waves, event horizon images, rotating spacetime, information paradoxes. The list keeps growing. Black holes seem uniquely talented at exposing gaps in human knowledge. They're not merely objects. They're questions. Questions written into the fabric of reality. Each discovery answers one mystery and creates several new ones. And that's one reason scientists love studying them. Because black holes continue reminding us that the universe is larger, stranger, and more imaginative than our assumptions. You drift quietly among the stars. The black holes around you fade into the darkness. Some are moving through the galaxy. Some are merging. Some are launching enormous jets. Millions remain unseen. All continue existing regardless of whether anyone is watching. Ancient monuments to gravity's power. And somehow, after everything you've learned tonight, they remain mysterious. Perhaps that's their greatest achievement. Not that they trap light. Not that they bend spacetime. Not even that they challenge our deepest theories. But that after decades of observation and discovery, they still inspire wonder. The stars continue shining. The galaxy continues turning. And somewhere in the darkness, another black hole is preparing the next surprise. Throughout this journey, you've encountered black holes as astronomers understand them today. You've explored what scientists know, what they've measured, what they've photographed, what they've detected through gravitational waves. But every time physicists learn something new about black holes, another question appears waiting nearby. Sometimes that question is practical. Sometimes it's mathematical. And occasionally, it's so strange that it sounds like it escaped from a science fiction novel. Tonight, you're visiting the frontier. The place where established science meets unanswered questions. Not because these ideas are proven. Many are not. But because black holes have become one of the most important testing grounds for understanding reality itself. The stars around you seem unusually distant. The darkness feels deeper. Ahead lies a collection of mysteries that scientists continue debating today. And that brings us to sleepy fact number 86. Some physicists have wondered whether black holes could contain gateways to other regions of spacetime. The idea begins with a concept known as a wormhole. A wormhole is a hypothetical shortcut connecting two distant locations. Imagine folding a sheet of paper. 2 points that were originally far apart suddenly touch. A tunnel through spacetime would work somewhat similarly. Instead of traveling across the entire distance, you pass through a shortcut. It's an elegant idea. Science fiction has embraced it enthusiastically. Physicists have studied it seriously. The challenge is that no evidence currently shows wormholes actually exist. And even if they do, keeping one stable may require forms of matter that have never been observed. Still, the mathematics remains fascinating. Some solutions to Einstein's equations allow structures resembling wormholes. And because black holes already distort spacetime so dramatically, researchers naturally wondered whether connections might exist. At present, nobody knows. The universe has not yet revealed the answer. But the question remains one of the most intriguing in theoretical physics. You drift quietly through the darkness. The possibility lingers. A hidden passageway somewhere beyond our understanding. A doorway that may exist only in equations. Or perhaps somewhere among the stars. Which leads us to sleepy fact number 87. Black holes may help scientists discover a theory of quantum gravity. This sounds like a very technical topic. And in fairness, it absolutely is. But the basic idea is surprisingly simple. Right now, physics relies heavily on two great theories. General relativity explains gravity. Quantum mechanics explains the microscopic world. Both theories work extraordinarily well. The problem is that they don't fit together perfectly. Most of the time, that's manageable. Black holes refuse to be most of the time. Inside black holes, gravity becomes incredibly strong. Quantum effects become important. The two theories must somehow work together. Yet scientists still lack a complete framework that combines them. A successful theory of quantum gravity would be one of the greatest achievements in scientific history. And black holes may provide the clues needed to find it. Imagine having two maps of the same city. Each map works beautifully. Yet neither shows the entire picture. Somewhere, a more complete map exists. Physicists suspect black holes may help reveal it. You continue floating through the cosmic darkness. The black hole ahead appears silent. Yet hidden within its mysteries may lie answers to questions humanity has pursued for generations. Which brings us to sleepy fact number 88. Some theories suggest the universe itself may behave in surprising ways near black holes. The deeper physicists investigate black holes, the more fundamental questions emerge. Questions about space, time, information, reality itself. Certain theoretical models suggest that spacetime may not be perfectly smooth at the smallest scales. Others propose that information could be stored in unexpected ways. Some ideas even hint that our understanding of space may be incomplete. It's important to remember that these remain active areas of research. Many competing theories exist. Evidence continues accumulating. Scientists continue debating. Black holes function like natural laboratories. Extreme environments where ordinary assumptions are tested. Again and again the universe responds by revealing something unexpected. You watch starlight curve around the darkness. Space itself seems flexible here, almost alive. The familiar rules still work, yet they feel closer to their limits. And the closer we approach those limits, the stranger reality becomes. Which leads us to sleepy fact number 89. The biggest mystery about black holes may still be waiting to be discovered. This is perhaps the most exciting possibility of all. History offers a useful lesson. Again and again, scientists believed they had uncovered the universe's deepest secrets. Then something unexpected appeared. A new particle, a new force, a new phenomenon, a completely new question. Black holes have already surprised humanity many times. They may do so again. Future telescopes will become more powerful. Gravitational wave observatories will become more sensitive. New theories will emerge. New observations will arrive. The discoveries awaiting future generations may be impossible for us to predict today. That's one of the joys of science. The greatest breakthrough is often the one nobody expected. Somewhere among the countless black holes scattered throughout the cosmos, another surprise may already exist. Waiting patiently. Waiting to be noticed. Waiting to change our understanding of reality. You continue drifting. The stars seem endless. The darkness remains calm. And the universe feels wonderfully unfinished. Which brings us to sleepy fact number 90. Even after everything we've learned, black holes remain among the greatest mysteries in existence. Think about what humanity has accomplished. We've measured their masses, photographed their shadows, detected their collisions, mapped their effects on surrounding stars, built theories describing their behavior. Yet fundamental questions remain unanswered. What happens inside the event horizon? What becomes of information? How does gravity ultimately connect with quantum mechanics? Do primordial black holes exist? Could entirely new kinds of black holes still be discovered? Nobody knows. And perhaps that's exactly why black holes remain so fascinating. Not because they represent the end of knowledge, but because they represent the beginning of new discoveries. You float quietly among the stars. The black hole ahead remains dark, silent, ancient, a shadow against the universe. Around it, galaxies continue turning. Stars continue shining. Time continues passing. And somewhere in laboratories, observatories, and universities around the world, scientists continue asking questions, searching for clues, building new instruments, developing new theories, trying to understand one of nature's most remarkable creations. The darkness never answers directly. It never explains itself. Yet somehow it keeps teaching us. And as you drift peacefully through the cosmic night, watching the stars glow beyond the black horizon, you realize something extraordinary. Black holes are not merely objects hidden within the universe. They are invitations. Invitations to keep exploring, to keep wondering, and to keep looking deeper into the darkness, where the next great discovery may already be waiting. You've traveled an extraordinary distance tonight. Not merely across space, but across ideas, across discoveries, across some of the deepest mysteries humanity has ever encountered. You've watched stars die. You've witnessed black holes collide. You've listened to ripples moving through spacetime itself. You've explored the possibility of ancient black holes born shortly after the Big Bang. You've wondered whether future civilizations might someday harvest energy from these cosmic giants. And now, as our journey begins approaching its final destination, there is one last place left to visit. A place humans can never truly see. A place hidden behind the most famous boundary in the universe. The event horizon. The point of no return. The ultimate frontier. You drift quietly through the darkness. Ahead, a supermassive black hole hangs against a sea of distant stars. The accretion disk glows softly around it. Light bends into impossible shapes. The universe itself appears distorted. And for the first time tonight, you decide not to stay at a safe distance. Instead, you move closer. Not recklessly. Not quickly. Just enough to imagine what the final journey might be like. This brings us to sleepy fact number 91. No one can observe what happens beyond an event horizon. This is perhaps the defining feature of a black hole. Everything we've discussed throughout the night ultimately leads back to this simple truth. The event horizon forms a boundary, a one-way border in spacetime. Crossing inward remains possible. Returning is not. Not because something physically blocks the way. Not because an invisible wall appears. But because every possible future path points deeper inward. The geometry of spacetime itself changes. Escape ceases to be an option. Imagine standing in a river. The current becomes stronger and stronger. Eventually you reach a point where every possible movement carries you downstream. No matter how hard you swim, the destination remains the same. The event horizon behaves somewhat similarly. Except instead of water, the current is reality itself. And once crossed, all roads lead inward. You continue drifting. The black horizon grows larger, silent, motionless, patient. A boundary separating the observable universe from the unknown. Which leads us to sleepy fact number 92. From the perspective of a distant observer, falling into a black hole appears strangely slow. Suppose an astronaut approaches the event horizon. From their own perspective, everything seems normal. At least initially. Their clock continues ticking. Time continues passing. The journey proceeds. But observers watching from far away would witness something remarkable. The astronaut appears to slow down. More and more. As they approach the horizon, their motion seems to crawl. Their image becomes increasingly redshifted. Dimmer. Fainter. Slower. Eventually they appear almost frozen near the edge. The astronaut continues inward. The distant observer never quite sees it happen. It's one of the strangest consequences of Einstein's theory. Two observers describing the same event. Both correct. Yet experiencing reality very differently. Black holes have a talent for making simple situations wonderfully confusing. You watch the imaginary astronaut approach the darkness. The stars reflect softly from their spacecraft. Time behaves differently depending on who is watching. The universe remains under no obligation to match common sense. Which brings us to sleepy fact number 93. The interior of a black hole remains one of the greatest unknowns in science. Everything beyond the event horizon is hidden from direct observation. Scientists can build models, develop equations, construct theories. Yet ultimately, nature keeps the interior concealed. The singularity predicted by general relativity lies somewhere within. But most physicists suspect our current understanding is incomplete. Quantum effects almost certainly become important. New physics may emerge. Entirely new ideas may be required. The truth remains hidden. It's worth pausing to appreciate how remarkable this is. Humanity has mapped the surface of planets, measured distant galaxies, detected gravitational waves from billions of light years away. Yet the interior of a black hole remains inaccessible. A mystery preserved by the structure of spacetime itself. The universe has many secrets. This may be one of its most carefully guarded. You drift quietly beside the event horizon. The darkness remains perfect. The mystery remains intact. And perhaps that's part of its beauty. Which leads us to sleepy fact number 94. Black holes challenge our understanding of reality itself. Most astronomical objects fit comfortably into existing theories. Stars are complicated. Planets are complicated. Galaxies are complicated. But black holes feel different. Again and again they force scientists toward the edges of knowledge. Questions about information. Questions about time. Questions about quantum mechanics. Questions about gravity. Questions about the very structure of reality. Some of the greatest unsolved problems in physics intersect with black holes. It's as though nature gathered its most difficult puzzles and placed them in one location. Convenient for organization. Less convenient for physicists. Yet every challenge creates opportunity. Every mystery invites exploration. And black holes continue inspiring some of the most ambitious scientific work ever attempted. You watch the stars bend around the darkness. The black hole remains silent. Yet its influence extends far beyond gravity. It shapes the questions we ask, the theories we build, the future discoveries we pursue. Which brings us to sleepy fact number 95. The story of black holes is still being written. This may be the most important fact of all. When Einstein developed general relativity, black holes were little more than strange mathematical possibilities. Many scientists doubted they could exist. Today we know they are real. We've photographed them, measured them, listened to them, watched them shape galaxies. And yet the biggest discoveries may still lie ahead. Future observatories will see farther. Future instruments will measure more precisely. Future scientists will ask new questions. Some mysteries will be solved. Others will undoubtedly appear. That's how science works. Knowledge expands. And with it, the horizon of mystery expands too. The universe always remains larger than our understanding. You float quietly in the darkness. The black hole hangs before you. Ancient beyond imagination. A monument to gravity. A challenge to physics. A reminder that wonder still exists. Around you, the stars continue shining. Galaxies continue turning. Time continues flowing. And somewhere beyond the horizon lies a region forever hidden from observation. A place where the universe keeps its deepest secrets. The journey is nearly complete now. Only a handful of facts remain. Only one final chapter awaits. And as you drift peacefully beside the great black hole, watching starlight curve around its invisible edge, you realize that perhaps the greatest lesson of all is not what we know, but what we still have left to discover. And so, our journey through the universe finally begins to slow. Not because we've reached the end of black holes. No one has reached the end of black holes. Not astronomers. Not physicists. Not even the universe itself. But because tonight, we've reached the end of our journey together. 100 sleepy facts. 100 glimpses into one of nature's most extraordinary creations. 100 reminders that reality is often stranger than imagination. You drift quietly through the darkness. The stars shine softly around you. The black hole ahead remains exactly as it has always been. Silent, patient, ancient, waiting. And somehow, after everything you've learned, it still feels mysterious. Perhaps even more mysterious than when you first arrived. This brings us to sleepy fact number 96. The more we learn about black holes, the more questions they create. Most discoveries in science answer questions. Black holes certainly do that. But they also have a habit of creating entirely new mysteries. When scientists first realized black holes might exist, the mystery was simple. Could gravity really become that strong? Then came new questions. How do they form? How large can they grow? What happens inside them? Can information escape? Do primordial black holes exist? Can gravity and quantum mechanics be unified? Every answer opened another door. Every discovery revealed another horizon. It's rather like climbing a mountain. You expect the summit to provide a final view. Instead, you discover an entire range of higher peaks waiting beyond it. The universe is remarkably good at extending the journey. You continue floating peacefully. The black hole remains ahead. Not merely an object, but a collection of questions wrapped in darkness. Which leads us to sleepy fact number 97. Black holes have transformed our understanding of the cosmos. A century ago, black holes were little more than strange consequences of Einstein's equations. Many scientists doubted they could exist in reality. Today they occupy a central role in astronomy. They influence galaxies, power quasars, generate gravitational waves, test fundamental physics, shape our understanding of spacetime. Few scientific ideas have traveled so far in such a short period of history. Black holes moved from mathematical curiosity to astronomical certainty, from theoretical possibility to observed reality. And throughout that journey, they repeatedly forced humanity to rethink its assumptions. The universe turned out to be stranger than expected. Again, which is becoming something of a pattern. You watch distant galaxies glow softly across the darkness. Many contain supermassive black holes. Many owe part of their history to those invisible giants. The universe would not look quite the same without them. And neither would science. Which brings us to sleepy fact number 98. Everything you've learned tonight came from human curiosity. It's easy to forget how extraordinary that is. No one can touch a black hole. No one can visit one. No one can directly observe what lies beyond an event horizon. Yet somehow humanity has learned an astonishing amount. Through mathematics. Through observation. Through imagination guided by evidence. Generations of scientists looked into the night sky and asked questions. Then asked better questions. Then built better instruments. Then searched for answers. The image of M87's black hole. The detection of gravitational waves. The discovery of Sagittarius A star. Each achievement began the same way. With curiosity. A simple desire to understand. The story of black holes is not merely a story about gravity. It's also a story about people. About our determination to learn how reality works. Even when reality becomes extraordinarily complicated. You continue drifting. The stars seem brighter somehow. Not because they've changed, but because you understand a little more about the universe they inhabit. Which leads us to sleepy fact number 99. You are made from the same universe that created black holes. This may be the most beautiful fact of all. The atoms in your body were forged inside ancient stars. The calcium in your bones. The oxygen you breathe. The carbon that helps make you who you are. All of it originated in cosmic processes unfolding long before Earth existed. The same universe that formed galaxies also formed you. The same laws of physics that govern black holes govern every atom around you. You are connected to this story. Not separate from it. Not merely observing from the outside. Part of it. A small but genuine piece of the cosmos becoming aware of itself. For billions of years, the universe evolved. Stars formed. Stars died. Elements spread through space. Planets emerged. Life appeared. And eventually, one tiny species began asking questions about black holes. It's a remarkable chain of events when you stop to think about it, though perhaps not too hard. This is, after all, a sleep story. You drift quietly through the starlight. The universe stretches endlessly in every direction. The black hole remains ahead. Dark, silent, timeless. And now only one final fact remains. Which brings us to sleepy fact number 100. The universe is far more wonderful than we can ever fully understand. For all our discoveries, mysteries remain. For every question answered, others appear. The cosmos continues expanding, continuing surprising us, continuing inviting us to explore. Perhaps future generations will solve the information paradox. Perhaps they will discover primordial black holes. Perhaps they will uncover entirely new phenomena beyond anything we've imagined tonight. Or perhaps the universe will reveal something even stranger. History suggests that's entirely possible. But for now, it's enough simply to appreciate the wonder of it all. The stars, the galaxies, the black holes, the immense story unfolding across billions of years. You float quietly beside the great dark horizon. The accretion disk has faded. The distant stars glow softly. Everything feels calm, peaceful. Still, the black hole no longer seems frightening, only mysterious, a reminder that some questions do not need immediate answers. Some mysteries can simply exist. And perhaps that's the perfect way to end our journey. Not with certainty, not with conclusions, but with wonder. The stars continue shining. The galaxies continue turning. The black holes continue waiting in the darkness. And somewhere, far beyond the edge of sight, the universe continues writing its story. For tonight, though, your journey is complete. The cosmos grows quiet. The stars drift slowly past. And the darkness, vast and peaceful, carries you gently towards sleep.